Alright, so this is chapter 14, which is acids and bases. And you'll remember we talked about, or I told you, because we're not really talking that much, at least face to face these days, um, that this is one of the chapters, chapter 13, 14, 15. They're all similar, they're all based on equilibria. They all are based on the same equilibrium expressions, equilibrium constants, and they're all based on equilibria, right? So you always have the same sort of relationships. Le Chatelier's principle is still true, so you can know in general which direction things will go. Um, Everything that was true in the last chapter, still true. Just ironically, the math actually gets a bit easier now that you have more details. For example, this is all going to be acids and bases. That limits a lot of what's going to happen. Alright. So, this is actually some review that we're going to start off with. You should hopefully remember something about acids and bases from last semester. They were actually introduced last semester. You had gotten a table that told you the general strengths of them and told you about pH and all these different concepts of acids and bases. This is actually the number one cause of students finding this chapter. Basically, I get two different types of students in this chapter. I have students that understand this chapter because they understand the material before it, and this isn't a problem at all. They go, oh wow, this is really easy. This makes chapter 13 seem like it was a lot harder because mathematically chapter 13 ends up being harder. The other type of student I usually get in this is students that their problem isn't this material per se. The problem that the second set of students usually have is they don't remember acids and bases at all. They don't remember anything about it. They don't go back and review it at all. And they just think they can build this up off of nothing. And so then they miss key details about these, like what is an acid, what is a base. They can't even start the problems in this chapter because they don't know any of the basic details. And the other part that those students oftentimes find difficult is the fact that they sort of skip chapter 13 because it's more difficult mathematically. They don't learn anything about it. They don't remember the products over equilibrium that I asked you to memorize from that chapter. And then they try to get into this chapter with nothing from those previous chapters, and it's impossible. If you don't know anything about those two previous chapters, you don't do any reviewing, you don't learn anything about them, this chapter will be a complete non-start for you. In fact, this chapter and the next chapter will both be non-starters for you. You just won't be able to do anything. So, understand that you may have to go back and review for this. Everything you're going to need is not self-contained in this chapter. That's why there's a prerequisite to this course, right? Okay, so Arrhenius concept. This is again review. Acids produce hydrogen ions in aqueous solution, and bases produce hydroxide ions. This has a very limited application as far as acids and bases go. This is probably the single most limiting definition overall. Another definition for this, acids and bases, is the Bronsted-Lowry model, which describes acids are proton donors. Remember, protons are H pluses. It's another way of describing a proton, a positively charged hydrogen. And bases will then be proton acceptors. You will notice in both of these cases, this is kind of like a yin-yang relationship. Acids and bases are sort of like opposites, okay? At least as close as you actually get to an opposite. There's no real such thing as opposites per se. Anyways, you have hydrogen ions here. If you combine them with hydroxide ions, that's H pluses with OH minuses, that would give you H2O, water. And so this concept's all about water here. Arrhenius concept, really when it comes right down to it, is all about water. Notice aqueous solution is in this definition. So this only accounts and only works in water. By the way, that gives you a common misconception most non-inorganic chemists have. A lot of organic chemists, biochemists, biologists, physicists, a lot of these folks have a misconception that you can do things like measure acidity in oil and it's going to be the same sort of thing as if you try to do it in water. And that's not right, actually. It's a very different concept when you talk about acids outside of water versus in water in aqueous solutions. Okay, so the Bronsted-Lowry model is another model. By the way, the Bronsted-Lowry model is going to show back up in organic chemistry. And there's one more model of an acid and base that actually was introduced last semester that you guys may remember or may not, which is the Lewis acid, Lewis base. And that one actually shows up in organic chemistry and is probably about 20% of organic chemistry if you understand Lewis acids and bases really well. It will be quite easy, actually, straightforward. Now, acids in water. When you have an acid in water, it is going to react with water. So remember, when you're talking about an aqueous solution, water is the molecule that there's more of, right? That's one that there's greater amounts of. And so when you have an acid or a base in water, the first thing it always reacts with is water. And what this means is all acid-base systems in water are always water mediated. That means that their pH scale is that 1 through 14. It's actually above 0 to 14. Most people don't realize that. But that is actually due to water. Water is what's setting that scale to above 0. You could have, if you did not have water mediated, these weren't happening in water, you can have acid that would be a negative in the pH scale. And the same thing goes with the 14. So the 14 is limiting for the base in water. If you were not in water, the pH 14 would not be your limit. You could go above that. So in water, whenever we talk about an H+, a proton being transferred, you're not really talking about an H+. An H+ is not bobbing around in solution and just wandering around. You don't have H+ wandering around. What you have in water is that water will act as a base if you put an acid like HCl in it. And so what happens is HCl will donate a proton to the water, giving you H3O+, which is called the hydronium ion. And then it will have its conjugate base remaining, which in this case is Cl-. And so what we see here is water is both an acid and a base. It is what is referred to as amphiprotic. Now, amphi meaning both, protic as in proton, right? And so right here we see water is the base reacting with an acid, giving you the conjugate acid and the conjugate base. And so all acid-base reactions, when it comes right down to it, happen through water. This has the most immediate and most important result being that rather than H+, even if we say H+ as a chemist, we're only saying H+ as a chemist because we're lazy. In reality, H+ in water, protons in water, always exist as hydronium ions. There's essentially none in the solution that would be in the form of H+. And so right here is an example general reaction for an acid in water. Now, this is the general acid dissociation reaction. What this means is literally dissociation is breaking apart. See that? You're left with the H+ part going onto the water and the A- part going by itself. Now you will notice that again, the A right here, this represents an anion, okay? Or you can call it an acid. Either way, it is a representation of that conjugate part of the acid that's left behind. So this could be like an HCl, an HBr, an HF, but it also could be something like um, HNO3. Okay? It could be a very great variety of things. It's just a general representation of an acid. And so the conjugate base is denoted by this A symbol right here. That's going to be the part that's left behind with a negative charge. The H plus will be donated, that being the Bronsted-Lowry definition of an acid, isn't it? And so this H plus gets donated to water, leaving you with the conjugate acid right here, which is the hydronium ion. Okay, so this is the slide, this is the area where the vast majority of students that have difficulties with this chapter are going to make their first mistake that is then going to harm them for the rest of the time that they try to learn this material. And that is, they will not pay attention to this and they will not be comfortable with this. They won't try writing it out, they won't try it out. Okay? So again, this is a great way of looking at acids. This told you a lot of information just from this general reaction. So all acids are going to react like this. You can use this for any acid. You can literally write out HA from now on and never actually write out the actual acid that you're using, okay? This tells you that you don't really care what the specific acid you work with is. All you care about is the fact that it's an acid and it has a Ka value. That's about it. When it comes right down to it, most acids simply won't matter their exact identity when you're doing problems. Now, this right here also tells you that this right here is always a liquid water, isn't it? Because you can't have a solution made of the same thing. I have actually had 3 groups in my time teaching labs that have tried to dilute a solution using the exact same thing. So let me give you an example of that. That would be like trying to dilute soda with more soda. Or dilute Everclear with more Everclear. Or even worse, dilute Fruity Punch with more Fruity Punch. It's not how dilutions work, right? And so, right here, you cannot have water diluted with water, right? You cannot have a solution of water in water. And so water will be a liquid always when you look at these. This tells you this is a pure substance, a pure liquid. That tells you that is not going to be in whatever equilibrium expression you happen to make from this. You will notice here that this acid and the definition of an acid is donating a proton. What that means is acids are always looked at as single donations of protons. Even if you have 3 protons to donate, you do it one at a time. And so every time you look at an acid, you're always going to do it 1 proton at a time. Okay, so the conjugate base is going to be the remains of an acid molecule after it loses a proton. How can you tell the acid? Well, it's the one that has an H plus to donate, isn't it? So this one right here has an H plus to donate. This one does not. This one lost its H plus. You can see that because it no longer has an H. And it is a negative charge where it was a neutral charge before, which means it lost a positive charge, didn't it? And so this is all of those things that you should have recognized when you just looked at this graphic, but many students tend to make the reverse, do the reverse when they do science classes. What I mean by the reverse is that in science texts, in science books, in science slides, in science in general, the graphics are the important part. Graphs, tables, these are the things that matter. In fact, in a good science textbook, you could just read the graphs, figures, and charts. You don't need to read the text at all, and you would be able to actually learn all the material from the book, if you can understand it. The only reason they have text in a science book is to clarify those graphs, figures, and charts. And that's because these are most things in science require some sort of media for you to understand, right? It's because you just can't see the actual objects. We're not talking about people that you can see, right? We're talking about molecules. You can't see those. Conjugate acid, this can be formed when a proton is transferred to a base. So right here we have a base. It has a conjugate acid. Conjugate meaning conjoined, right? And so this is conjoined with the base, conjugate acid. Again, how do you tell which one's the base? Well, it's the one that's going to gain an H+, right? And so this has gained an H+. How can I tell these two are related? Well, there's the oxygen. This one doesn't have an oxygen. That one does. So these have to be related. This has an A. That has an A, right? These have to be related. Alright, so a conjugate acid-base pair. These are going to be two substances that are related to each other by accepting and donating a single proton. Now notice that all of this was based on single protons. And so when you look at acid bases, again, these are always going to be looked at through the lens of this definition, which is donating a single proton at a time. So an equilibrium expression, this is the same thing over. Just notice, because we have defined our definition for acids as donating a, which means one, proton, we have now locked in our equilibrium expressions to have ones here. Did you realize that when you thought about that? That because we defined this as always being one proton being donated at a time, we have defined our Kas for these equilibriums as always having it to the first order, the first power. And so we have automatically now made these equations 10 times easier. We no longer have to deal with second, third, fourth powers, right? And some bizarre math that we have to do with, some really long workouts sometimes, right? So we have greatly simplified all of these problems now. This right here is, again, a K, which is an equilibrium constant. This is the equilibrium expression, again, products of reactants, right? We will almost always simplify the hydronium ion by writing it as H+. Because, as a chemist, you should understand H+ in an aqueous solution means hydronium, okay? You shouldn't need this to be written out. You should just be able to look at that, and you should see this. All right, now, Ka, this is the acid dissociation constant. Literally what's happening is you are splitting up an acid, Ha, you're donating the proton off, and you're leaving behind the conjugate base. Literally disassociating an acid, right? And so the name makes perfect sense if you think about it a little bit. And this right here, K is a constant, it's sub A for acid. So this is Ka, which means acid dissociation constant. This gives you a lot of hints when you look at it. So water can be emitted from this acid dissociation constant. Remember that because it is a pure liquid, it goes to unity and does not get written into this equilibrium expression. It's actually part of the equilibrium constant, if you remember. So that doesn't affect the equilibrium position. So let's write the simple dissociation, which again would be the ionization reactions, where we are giving off an H+ and leaving our conjugate base, right? We can omit water for each of these following acids. So let's go ahead and do A first. So right here we have HCl. This is going to be the acid dissociation reaction, giving us H+ and Cl-. If we had put water in here, yes, it would have been plus H2O, like some of you are probably thinking and want to do, which is fine. That's why I had the emitting water in here, right? So again, H+ comes off, we're donating an H+, and we're leaving behind a Cl-. Again, these are all aqueous solutions here. All right, so this one right here, which is acetic acid, again, we have one of these H's that is different than the others. Hopefully you can recognize that there's one split off. The reason that's split off is this is actually bounded over here on the oxygens. That is an acidic H+. If nothing else, you probably should recognize this because it is the single most used example acid for a weak acid in science, period. I promise you, you have seen this right here at least a dozen times in your General Chemistry 1 career alone. So you have H plus here, again, an acid, you're giving off an H plus, and then you leave behind the rest that's not a single hydrogen, and you give it a negative charge, just like so. Again, we see another example. So again, we're going to split off one of these H's. We're always going to choose the ones that are on electronegative atoms, never the ones on carbons. Why do we do that? Well, again, these electronegative atoms can hold onto electrons better. And so right here we see this actually has a positive charge already. And so we're going to write H plus here. We've taken an H, so this will be H2. We have taken away a plus, so this will have no charge here. Notice that's a bit different. This was actually, this right here is usually considered a base. This is an amine. This is a weak base. And this is actually the reverse reaction of an acid reacting with a base. So this is kind of an interesting thing, right? Remember that these are actually flipped for an acid versus a base. All right, so so this one, next one right here, which is D, which is the hydrated aluminum 3 ion, which is this right here. Okay, so in D, this one looks complicated. It's actually quite simple if you can concentrate on your meaning of your Ka. So you're removing a proton, right? Which can only come only from one of the water molecules here. You only have those water molecules that have hydrogens, right? The aluminums certainly aren't hydrogens. And so this is going to leave you with one OH minus, which is one of the waters without its H plus, and then 5 of those waters will remain as waters. And so right here we have our 6 waters right there. And so this is going to donate an H plus. We split off one of these H pluses, leaving us with an OH right here, which is one of those. And then that leaves us with 5 of these remaining, so we put a 5 here. Notice that this was a positive 3 charge. We've removed one of the positive charges to give it a 2 plus charge here. So you see that it doesn't actually have to be difficult and hard. In fact, this is supposed to be easy and simple. The only reason it will ever become hard is because you make it hard. Because you think it should be hard, because it's chemistry, right? So this is not actually something that needs to be difficult. Now, Bronsted-Lowry model. This can be extended to reactions in the gas phase, actually. Notice in the Bronsted-Lowry model, we did not actually have aqueous in there. It was only the Arrhenius definition of an acid and base that had aqueous in that definition. And so you can have gaseous HCl and gaseous ammonia reacting to form things like NH4Cl, which is actually a salt. And this is actually interesting because this is actually what happens a lot in atmospheres around like cities and industrial areas. So it's kind of funny because some of the pollution actually gets fixed from cities with a lot of cars by industrial areas around them, which have quite a bit of ammonia, or a farm area around them, which has a lot of ammonia too. So it's an interesting thing if you're curious. Anyways, this is a base reacting with an acid to give you a salt, which is the typical acid-base neutralization reaction, actually. All right, so what is the equilibrium constant for the following reaction called? Now, let me point out real quick that I'm going to do a lot of problems in this chapter. There's a lot of them here. And that's because conceptually, this chapter really is not supposed to be challenging. It shouldn't be challenging. The challenging part is the fact that you have to remember stuff from 2 previous chapters. That's about it. This chapter really doesn't have a lot of challenging stuff in it. The reason that people usually have trouble with this chapter is they just fail to practice. They fail to look at the previous information and fail to practice. That's about it. And so practice, practice, practice. That will give you the ability to do this and do it consistently. What is the equilibrium constant for the following reaction called? Well, right here we have our acid, don't we? Here we have, well, our conjugate base. We're reversed. So what happens when we reverse a reaction? What do we do to its equilibrium constant? Well, we take the inverse of that. And so this really was a question from chapter 13 and just applied to new material. Identify the Bronsted acids and bases in the following equation. A for an acid, B for a base. And so right here, well, what are we looking at? Again, if it's an acid, it is going to lose an H plus, right? If it is a base, it is going to gain an H plus. And so right here, we see this has an H, SO4, see that? We look at these parts and then see if it kept its H plus. Don't look at the H, because that's the thing that's being transferred. That's the one you don't want to look for. Okay, so we have our HSO4 here. This has an SO4, it lost an H, didn't it? And so that had to be our acid, that has to be our conjugate base. And over here, we had one H, we now have two of them on the PO4s. Now, that means that this was a base, and it became a conjugate acid. So we have BA, AB. By the way, they were typically going to be exchanging. So when we look at this, what was the base will of course become the conjugate acid. What was the acid will of course become the conjugate base. Alright, so this right here is the strength of an acid we're going to look at here. And so if you remember your electrolytes from last chapter, the strong electrolytes were very likely to dissociate, right? And so the strong electrolytes dissociated completely in solution, while the strong electrolytes only dissociated partially in solution, and much of them remained together. Now, a strong versus weak acids and bases is going to be the exact same thing. So a strong acid, in this case, the equilibrium will lie so far to the right that it almost goes to completion. And so you would expect a strong acid to almost completely dissociate. Typically, they're thought to completely dissociate, and we use those numbers for them completely dissociating. A weak acid is only going to partially dissociate. And so you'll have an equilibrium, and these will be a moderate value where much of it still remains as this form right here, which is the acid together, and some of it will be the conjugate base form right here where it has donated its proton. So the weaker the acid is, the further over on this direction the reactants, the acid will stay together. That's weaker. The stronger the acid is, the more over to this direction it is, the products, where it has donated its proton. Notice this has nothing really to do with reactivity per se. Okay, HCl is your stomach acid. That is a strong acid. HF is an acid that can react very close to anything, nearly anything, and that is actually a weak acid. It's just very, very reactive because of fluorine. All right, so strong and weak acids. A strong acid, again, is going to be nearly completely dissociated, whereas a weak acid will stay together, mostly be undissociated, which means most of it will stay together. So the various ways to describe your acid strength is right here. This has in general, just what I just talked about in a nice tabular form. So there's also different types of acids that we can talk about. There's the diprotic acids. This is composed of two acidic protons, so every molecule will have two H pluses it can give off. Usually the first one would dissociate completely if it is a strong acid. Though there are weak acids, of course, diprotic acids, that do not, the first acid, H plus, does not come off completely. However, sulfuric acid is an example of a strong diprotic acid. This first H plus, one of these H pluses, comes off completely, is a strong acid. The second one is a weak acid. You do not have all of that H plus coming off. Now, oxyacids, this is going to be acidic proton that's attached to an oxygen atom. We've actually already seen several examples of this. It's a fairly common, it's actually one of the most common acids. And it's the most, almost the only organic acid out there, the only biological acids. You'll typically find them being oxyacids. So here's some examples of oxyacids. We have nitric acid, of course, phosphoric acid. We also have sulfuric acid. Those are all oxyacids. We have, I know that I didn't mention monoprotic acids here. That's actually the acids you're most common with. Mono meaning one proton. That's like HCl, monoprotic. Right here, this is a triprotic acid, tri meaning three. So triprotic, three H pluses. Organic acids, this is going to contain a carbon atom backbone. So right here we see the carboxyl group. This is a more specific example of the oxyacids. And the reason it's more specific and it's so important is the organic acids, of course, are pretty much all of your biological acids. So they are the most common biological acids. These are typically weak acids in nature. These are things like acetic acid, benzoic acid, formic acid, etc. The hydrohalic acids, these are all going to have hydrogen attached to a halogen atom. Now, this acidic proton is attached to the atom other than the oxygen. It has to be attached to the halogen atom. And so this will be HCl, HBr, of course HCl being your stomach acid. Monoprotic acids I mentioned actually, this is going to have one acidic proton. So right here we see an example of, this has one acidic proton, so it is not a monoprotic acid. Right here we see another one that has one acidic proton. Again, the proton attached to the oxygen is the acidic proton. All right. So this right here is Ka values. This is how you typically find them in tables like so. And so this is some different common monoprotic acids, their names, and their values for their Kas. All right, so if we use table 14.2 right there, that has those Ka values. Let's arrange these species according to their strengths as bases. So what we're looking for here is the stronger an acid, the weaker its conjugate base. The stronger the conjugate base, the weaker the acid. All right? And so what we're looking at here is these Kas, remember, they are products of reactants, is what their equilibrium expressions are. And so when we look at these Kas, these are telling us how strong an acid is. By the way, if you forget, you can actually figure it out just from, you kind of know what's a strong and weak acid. Right here we have our weaker acids, right here we have our stronger ones. Most people have a fairly good direction for weak versus strong acids after they do a few of these problems. All right, so our K, of course, the smaller this value here, the -2, is a larger value overall, right? 10 to the -4 is actually a smaller value. 10 to the -10 is an even smaller value. It's an extremely small value, actually. And so what we're looking at here is The stuff on the top is your stronger acids, not strong acids. They are stronger. Down here, these are the weaker acids. And so H2O, F minus, Cl minus, NO2 negative, and Cn minus. What we're looking at is reverse. So we can list these conjugate bases in reverse of the strength of their acids. So if we list these in reverse of the strength of their acids, we will see that Cl minus, which is HCl as an acid, is the strongest acid, right? So it will be the weakest base. That's why HCl is such a strong acid, is Cl minus is such a weak base. H2O is actually what we judge everything off of. So H2O is one of the weaker bases when it comes right down to it. OH minus is the definition we judge strong acids off of, or strong bases off of, and H3O plus is actually the cutoff and definition we define strong acids off of. And so the H2O, this has to be weaker than the conjugate bases of all the weak acids. If it wasn't, those would no longer be weak acids. Those would have been strong acids. And so what we're going to do next is we'll then use the table. And so we look at the table. The Ka for HF is greater than the Ka for HNO2, which was greater than the one for HCN. And so we take our conjugate bases for those. We flip these arrows, and there we go. So F minus has to be a weaker base than NO2 minus, which has to be a weaker base than Cn minus. So if we combine these two factors, we get this order right here, which is Cl minus is weaker than H2O, which is weaker than F minus, weaker than NO2 minus, weaker than Cn minus. So amphoteric, this is a substance that behaves either as an acid or base, like water. Water is the perfect example of something that is amphoteric. There are, of course, other examples though, okay? Typically things like amines, some amines can act as amphoteric substances. There's also several other different substances. Frankly though, the only one you're going to find and use a lot is water. Until you maybe get into a higher level chemistry, in which case you get to see more. Now, this is depicted in the autoionization of water. So water is both an acid and a base. What that means is that if you have water and it's with itself, like, glass of water, you can actually have water donate a proton, one water molecule donates a proton, to another water molecule, which will then act as the base. And so water will actually autoionization, transfer a proton from one water molecule to the other, which will leave you with hydroxide ion and a hydronium ion floating around the water. And so even water just sitting around, there's a little bit of acidity, there's a little bit of basicity. One water molecule, of course, will act as an acid, one will act as a base. And so right here we see the reaction for this. This is the autoionization reaction for water. This will happen in any water source, any water at all, whether it's a solution, whether it's pure water, doesn't matter. Any water will do this, as long as it's in its liquid form. So right here we have two water molecules in their liquid form, and one is going to donate a proton to the other, right here, which is your hydronium. And this other one will be hydroxide. Notice that these are different compounds, they have different formulas, and so they are solutes dissolved in water now. Now, this is your equilibrium expression. Notice the only things that are not pure substance are on your products. And so you get a K, which is an equilibrium constant, that equals the hydronium ion times the hydroxide ion concentrations. And you don't have to do any denominator because these are pure water. They're pure liquid. This right here, this is a very special value. This is called the ion product constant. Typically, people actually call it the dissociation constant for water. And what this always refers to is the autoionization of water. And this is going to be a constant for a given temperature of water. Okay, so for 25 degrees Celsius, you'll typically have that same kW all the time. And there's very little difference if you're off 1 or 2 degrees. So you can pretty much just use that for everything. So no matter what the solution contains, your product of H plus and OH minus must always equal the total of Kw, which is because water has its own equilibrium. If you add more H plus, what happens? Well, Kw never changes. Remember, it doesn't matter where you start or stop, where your equilibrium positions are. Kw, the Ks, are always the same. And so, if you add H plus to water, it's going to push your equilibrium towards making more water, right? If you add OH minus to water, what's going to happen? Well, it's going to push your equilibrium towards making more water, right? And so what happens is every time you add an acid or a base, H plus or OH minus, these are always going to give you the same Kw, which is 1 times 10 to the negative 14 at 25 degrees Celsius. Notice the 14 value here, our pH scale is 0 to 14, right? That's where the 14 comes from, because we're doing it in water. Okay, so Kw equals, again, the concentration of H plus times the concentration of OH minus at 25 degrees Celsius, assuming you have neutral water, just water with nothing else in it. You're going to see that the concentration of H plus would equal the concentration of OH minus if we're neutral. And that means that the concentration of H plus will be 10 to the negative 7. The concentration of OH minus would be 10 to the negative 7 if we are neutral, giving you a total Kw of 10 to the negative 14 at 25 degrees Celsius. Yes, if you are lower than 25 degrees Celsius or higher than 25 degrees Celsius in temperature, this Kw will change. It changes fairly slowly, not extremely fast, but it does change because it is temperature dependent, just like every other K. Now, a neutral solution will always have the H plus equal the OH minus. In this case, that would be 10 to the negative 7 for each of those values. An acidic solution is defined by having the concentration of H plus be greater than the concentration of OH minus. A basic solution would be the concentration of OH minus is greater than the concentration of H plus, just like our Arrhenius definition of a base and acid before, right? All right. So at 60 degrees Celsius, our value of Kw would be 1 times 10 to the negative 13th. So let's use the Chatelier's principle to predict whether the following reaction is exothermic or endothermic. So remember, our Kw is product of reactants. And so that means that this Kw right here is a very small number. It's, again, a larger number than it was before, right? Which is 10 to the negative 14 before, it's now 10 to the negative 13. And so what does that mean? Well, that means if this value has went up, our products are going up, and our reactants are going down as we are adding heat energy, which means temperature, increase in temperature, right? And so if our products are going up as we add heat energy, that would indicate this is, anybody guess it, endothermic. Very good. All right, so the next thing we need to do then is we need to use this value right here with our equilibrium expression and figure out what concentrations would work for this. So we're looking here for a neutral solution. And so right here we have our equilibrium expression, H plus times OH minus, equals our Kw at 60 degrees. This right here is going to be for a neutral solution. So in a neutral solution, the H plus and OH minus have to be the same. That means that this right here, these are the same terms. So what we have is an x squared equals 1 times 10 to the negative 13. Another way of saying that is the OH minus concentration equals the H plus concentration. These will equal the square root of our 10 to the negative 13, which is 3 times 10 to the negative 7th molarity. So both these concentrations, again, are equal. So let's consider the reaction of an acid and water. If A minus is better base than H2O, which way will the equilibrium lie? So this is going to lie in the left. And the reason for this is what you're evaluating here is the better base means that it will accept an H plus better, right? So if A minus is a better base, it will accept an H plus better, giving you this. H2O is a worse base, so it's less likely to accept an H plus going this direction. And that means we've been told that this is going to head in this direction. We will favor our left, or our equilibrium will lie to the left. Let's consider this right here. Again, this reaction. If A minus is a better base than H2O, HA is a weak acid or a strong acid. So if our A minus is better base than H2O, that means this has to be a weak acid. Again, this is actually the same problem as before. We're just looking at whether lying to the left means a weak acid or lying to the right. And of course, lying to the left, meaning it does not donate H plus very well, is a weak acid. Lying to the right, meaning it would donate H plus very well, would be a strong acid. So this right here again, same sort of thing. If the A minus is a better base than H2O, is the value of Ka greater or less than 1? So the first thing you got to remember is Ks are always products of reactants, right? So again, it's the same problem. We're just now looking at Ks. So A minus is a better base than H2O. That means that this is going to be going to the left direction. That means you'll have less products, more reactants, giving you a K that is less than 1. HF and HCN are both weak acids, but HF is a stronger acid than HCN. Consider the following reaction and determine the value of K. So HF and HCN are both weak acids, of course. HF is a stronger acid than HCN. What does that mean? Well, we have HF here acting as an acid in this direction. In this other direction, going from right to left, we have HCN acting as an acid. So if HF is a stronger acid, that's going to mean it's going to go more towards this right direction. And what that means is you'll have more product. More product over less reactant will give you a K that is greater than 1. Which of the following graphs best represents a plot of H plus on the y-axis versus OH minus on the x-axis for an aqueous solution at constant temperature of 25 degrees? That's going to be, sorry about that, I noticed I had the wrong one highlighted. Had to go back. Okay, so remember that your H plus and OH minus, these are always inversely related, right? And so anytime you have a larger amount of H plus, you have to have less OH minus. Anytime you have a lower amount of AOH minus, you have to have more H plus. They're always inversely related. And so you have to be D right here, which are inversely related. None of these other ones would make sense. Having more H plus doesn't give you more OH minus. It wouldn't give you a constant all the time, not changing. And it can't be a logarithmic relationship, because that would mean you'd have one that gets more than the other, has a bigger influence than the other. They have an equivalent influence. They're inverse. So as water is heated, its pH decreases. This means that, well, none of these are correct, are they? This is the water is no longer neutral. Well, if the water is neutral, it's neutral. That doesn't mean anything that the water heating its pH decreases, pH is just a concentration of H plus. So neutral, on the other hand, is the concentration of H plus equals the concentration of OH minus. These aren't actually related directly. You may be used to the fact that at 25 degrees Celsius, pH 7 would be the pH of a neutral solution. That's what a lot of people get used to, and they get a little tripped up on this. So anyways, the water, yes, it's still neutral. Doesn't matter that it was heated. It doesn't matter the pH decreased. It's still neutral. It didn't tell you that it had an acid or base. It's just the water being heated. The H plus isn't changing versus the OH minus. They're still the same. And so these two don't make any sense. And it can't be any of those, so it has to be none of them. HA and HB are both weak acids in water, but HA is stronger acid than HB. Which of the following statements will be correct? Alright, so if HA is a stronger acid than HB, well, that tells you a lot about this A versus this B, right? A, therefore, has to be a weaker base than B, doesn't it? But they also told you something right here, and that's they are weak acids. That means that both of these, their conjugate bases, are both stronger than Cl minus, okay? Because they're weak acids. Cl minus would have given you a strong acid, so if it would have been worse of a base than Cl minus, it would have been strong acids. All right, so we look through all our options. What we see is B right here. Let's go ahead and check that, just to make sure. B minus is a stronger base than A minus. Okay, so we saw that HA is a stronger acid. So this is the reverse. That's good. That's what we wanted to see. Which is a stronger base than H2O. Okay, that also has to be true because otherwise it wouldn't be an acid, would it? And this is a stronger base than Cl minus, which again has to be true because these are weak acids. The value of Ka for 4.00 molarity weak acid HA is blank. The value of Ka for 8 molarity weak acid HA is what? Alright, so if you remember anything about your Ks, you remember that the position does not matter. Whatever concentration you start with, whatever concentrations at equilibrium, for any given equilibrium, that Ka at the same temperature is the same. So Ka is Ka. It doesn't matter 4 molarity, 8 molarity, 12 molarity, none of that matters. So the pH scale, many of you probably do not remember much about the pH scale. This is going to help represent the solution acidity. This is a log scale that's based on 10. And so pH actually equals the negative log of the H plus concentration. Now, how do you get the pH if you have the H plus concentration? Well, you take the negative log of that H plus concentration. That would give you your pH. If you remember how to do an anti-log, then this becomes very easy to undo as well. So let's say you had a pH. So you had a pH of 7. How would you undo that? Well, you would take 10 to the negative 7. That would give you your H plus concentration. So as pH decreases, the H plus concentration would increase. Because again, you take 10 to the negative pH would give you your H plus concentration. And that means that 10 to the negative value actually is getting smaller and smaller and smaller the bigger that negative value gets, right? So for a solution where your H plus equals 10 to the negative 7, you're going to find out that your pH would equal 7. Because again, you put in this 10 to the negative 7. This would leave you this negative 7 right here from the log. And this would again give you negative times a negative 7. Now, With significant figures, you may have noticed whenever we talk about science, significant figures is actually quite important. The reason for that being is it reflects how well measured our values are. So our number of decimal places in the log is going to be equal to the number of significant figures in the original number. So for example, right here, we have two significant figures that are going to go into our log. Once they come out in the form of a pH, these will be the number of decimal places we have. So this will be 2 decimal places after the 9. Right here, this is your different log scales and our acidity versus basicity scale. And so, we of course have pH, right? And that P actually always means the same thing anytime you see it. So that small p actually means negative log of whatever else is listed. So pH, that was negative log of the H plus concentration, right? pOH then would be the negative log of the OH minus concentration. And pK would be the negative log of the equilibrium constant K. So again, these are going to be used so we have a much easier way of writing these down and using these numbers, right? Because you may have noticed many of these numbers are actually quite long to write down. Now, here we see the pH scale going from 0 to 14, which is the water pH scale. Here we see the neutral, acidic versus basic at room temperatures. So at room temperature, pH 7 would be considered neutral. And this would usually be pure water is just usually is about there. pH 7 should be pure water. Of course, in experimental measurements, everything's a little off. Blood would be slightly above this. Milk would be slightly below this, slightly acidic. Black coffee is usually slightly acidic here. Here we see stomach acid, lemon juice. These are all acidic. That's what gives them their flavors, the bitter flavor. Up here we see bases, ammonia. That's the household cleaner you use on a lot of your probably countertops and such. And NaOH, which would be lye. These are very basic, and that's actually how they kill bacteria. Here we see baking soda, that's basic, seawater is basic, etc. This gives you a general idea of the pHs and the different things around you. Now remember, when we look at a pH scale, every 1 unit is going to be a 10 times change in the H+. What does that mean? Well, pH 1 is 0.1 molarity H+. If we go up to pH 2, that's 100 times less. So you'd be talking about 0.01 molarity H+. So when we talk about a 4 pH units difference, that's a 4,000 time difference in concentrations. Okay, it's actually a huge amount of difference. It's logarithmic, right? Huge change every single time you make a 1 pH scale change. So a pH meter, this is going to be an electronic device with a probe that can be inserted into a solution of an unknown pH. This probe contains an acidic aqueous solution. It's enclosed by a glass, it's actually they call it special glass membrane, but it's not actually that special. It's actually fairly easy to make. That permits the migration of H+ ions across it. Now, this electrical potential results if the unknown solution has a different pH from the solution in the probe. Now, I just told you some information that probably hasn't sunk in yet. It had important consequences. This tells you a few things about pH probes, actually. So first off, they work by electricity, right? So electrical potential. So if you stick a pH probe in an oil, which doesn't conduct electricity, or water that's too pure, which also doesn't conduct electricity well, it won't work because you need an electric potential across it. You need electricity to actually be able to transfer. The other part is, well, what happens if you leave a pH probe out to dry? Well, inside that glass membrane, right, there's an acidic aqueous solution. If you dry that out, it's not going to be aqueous anymore, right? it won't have the proper concentration either. So you actually always need to store these in an acid. You cannot store these in DI water, and you cannot store these out in the air to let them dry out. It'll actually destroy the probes, and then you have to do a lot of work to get them reestablished. It takes usually a couple months. The other thing that I've shown you here is these have glass membranes at the end. Is glass particularly a great thing to smash against something or stir? No. One of the most common things I see people do when they first use pH meters is they smack the ends of it onto countertops to dry them. And then they break the probe underneath, right? And then bam, you're out depending on how good of a meter it was, it could be anywhere from $30, that's pretty much a minimum. Typical meters, most meters are like $60 to $80. And the very, very expensive, very nice ones can be $300, $400. I've seen one that's $1,000, but that's very, very high profile. Anyways, right here we see a pH meter being used to measure the acidity and basicity. Here we're measuring vinegar, it's an acid, and so we see a pH less than 7. Right here, ammonia, that's a base, and so it's pH of 11.37. This is a very old looking pH meter. Most pH meters now have a little thing up here like that, and that's the whole pH meter. They all have this though, which is a glass bead at the end with little coverings that are plastic to try to protect them. Alright, so let's calculate the pH and pOH for each of these following solutions at 25 degrees Celsius. So 1 times 10 to the negative 3 molarity, OH minus, and then 1 molarity, OH minus. So again, you can do this 2 different ways. So you may have noticed that, yes, Kw equals the concentration of OH minus times the concentration of H plus. That's the first way I'm going to show you how to do this. It is not actually the easiest way in my opinion, but it is a way to do it. And so you, of course, just take your Kw, 10 to the negative 14, at 25 degrees Celsius, divide it by your OH concentration that was just given to you right here, and this will give you your 10 to the negative 11 H plus concentration. You're going to take the negative log of that 10 to the negative 11 value, and that will give you a pH of 11. If you're planning on taking the MCAT and trying to become a physician in the future, you need to work on learning how to do logs in your head. By the way, logs in your head are not that hard. This is base 10, so all you're doing is just extracting this number here. And that will give you a pretty good roundabout answer. However, for this class, I would highly recommend using your scientific calculator. All right, so right here we see the other way of doing this. You will notice the other way of doing this is actually much faster to do. And so what you can do is, instead of getting your OH concentration, or your H plus concentration first from the OH concentration, what you do is you just take your OH concentration, you get a pOH. And so the negative log of that OH concentration you were given before is, well, 3. This gives you a pOH value of 3. Now, let me say that if you paid attention to that chart before, many of you probably didn't see it for long enough to really get it down, but the pKw would have been 14, right? What that means is that 14 at 25 degrees Celsius, your pH plus your pOH always has to equal 14. And so if we take this pOH value, we can subtract it from 14 and get our pH value. And so that's actually a much faster and easier way of doing things. You will notice that your pH and your pOHs at 25 degrees Celsius always have to add up to be 14. All right, so we go ahead and do the little bit longer method way because it's a little bit conceptually easier. Right here, we get the Kw divided by the H plus concentration, which is 1, which means you have an OH minus concentration of 10 to the negative 14. And that's going to give you, well, a pH. You take the negative log of this 10 to the negative 14. That will give you our I skipped a part. Excuse me. Anyways, that gives you a concentration. Oh, we're doing OH minus. So that will give you a concentration of our PaOH of 0 for our H plus concentration, which is 1. Our POH concentration then will be 14. For a concentration, or a POH will be 14. For our OH concentration of 10 to the negative 14, which is negative log of 10 to the negative 14, which we did before. Right here, again, our pH plus our POH always has to equal 14 at 25 degrees Celsius, and so we see these equal 14 together. This right here was the concentration we were given, that 1. This one was the one we figured out right here. Alright, so let's go ahead and do the math to show you why you have that 14. So you remember that KW equilibrium expression? Well, that KW, which was at 25 degrees Celsius, 10 to the negative 14, right? Well, that equals the H plus concentration times the OH minus concentration. Now, being as this is an equation, you can go ahead and take the log of it. So if we were to take the negative log of both sides, we would get this expression right here. And how do you split up things that are logs? Well, this is how you do it. When you take the log of KW, that's just the log of KW, right? The log of this can be split up as the log of H plus the log of OH minus. That's how you represent these two things would be multiplied inside of the log. And so if we took the negative log instead, we just put negatives everywhere in front of that. Now, you'll notice this negative log of KW, we've defined that as being PKW, haven't we? Negative log of H plus, well, that is pH. And the negative log of OH minus is the POH. And so we see here that the PKW, which at 25 degrees Celsius is 14, would be equal to the pH plus the POH. So our KW, which again 10 to the negative 14, 25 degrees Celsius, is of course that 14 right there. Alright, so the pH of a sample of human blood was measured to be 7.41 at 25 degrees Celsius. So let's calculate the POH, the H plus concentration, and the OH minus concentration for the sample. And so, right here, excuse me. Alright, and so here you're going to see that when it comes right down to it, because you know so many other factors about water, now you only need this one pH value here to get all these other concentrations from it and everything else. And so, of course, we have a pH of 7.4, right? And so pH plus POH has to equal 14. And so, of course, we take 14 minus 7.41. And that will give us our value for our pH. Our POH. Excuse me. Which is 6.59. Alright, so the next thing we're going to do here is we're going to find our H plus concentration and our OH minus concentrations. So what you do for H plus and OH minus concentrations, they're very similar on how you do the problem. You're just going to take 10 to the negative pH, that's going to be your H plus concentration. So we take our 10 to the negative pH, which would be similar to taking antilog. It's the same thing, actually, that's what an antilog is. And that will give us our H plus concentration, which is 10 to the negative 7.41, which was our pH. And that will give us 3.9 times 10 to the negative 8 molarity, which is our concentration then of H plus. Our POH then, we take that and we're going to plug that into the 10 to the negative POH here, that's our POH value. And that is going to give us our OH minus concentration, which is 2.6 times 10 to the negative 7th molarity. Excuse me. So right here, this is just a simple practice problem. You can get a bunch of practice on this. It should be something you should be able to do this very, very easily, very quickly. Otherwise, you're going to find you are going to struggle on this, and you're not going to be able to do anything else in your exams. It'll just make everything exponentially more difficult if the easy stuff is difficult. So right here, of course, we just take pH plus POH equals 14 every time. So these will always have to add up to 14. So that would be adding up to 14 right there, 7.14. The H plus concentration, we take 10 to the negative pH, which is that. The OH minus concentration, we take 10 to the negative POH, which is that. Every time we get these values, we can look at our pH at 25 degrees Celsius. If it is lower than 7, then we are going to have a value that is acidic. If it is greater than 7, we will have a base. And if it is 7, that is neutral. And so there we see the answers for that. It'd be a great opportunity to practice if you are still having some trouble with that. You have 100 milliliters of a solution of hydrochloric acid that has a pH of 3. You add 100 milliliters of water to this solution. So what is the resulting pH of this solution? Well, in this case, right? All right. Okay. So in this case, you have several different options here. None of these are actually correct, but your pH has to be less than 3. You can't have, okay, so pH is a measure of H plus concentration, right? So what you have here is a dilution problem, meaning that your H plus will be a lower concentration than your, then it's not going to be, okay, let me go step back a second. Excuse me, let me get a drink. Sorry about that. I've been sick. I don't think it's any COVID or anything. I just think I ate something that I should not have eaten for like the last couple days. Anyways, this is, okay, so you have your pH, it's 3. You are then mixing it, this hydrochloric acid, right? You're mixing it with water, you're diluting your acid, so this is going to be less acidic, which means it is going to have a pH somewhere that is closer to 7. Now, pH is not a scale that is linear. pH is factors of hundreds difference, right? Or factors of 10 for every pH unit. And so when you look at these, you cannot get from this change in constant pH right here without doing more work. You cannot get any of these numbers here. So for example, an average of 3 and 5, it doesn't really make sense here because it's not a linear scale, right? pHs are just not linear. And so you are not going to get an average of those. Your pH of 10, that is definitely doesn't make any sense. A pH of 3 also doesn't make any sense because this would indicate you have the same amount of H+. This would indicate that you went basic somehow. And so it has to be a pH that is greater than 3. Apparently I had the wrong one bolded. Excuse me. Okay, so the pH of a solution at 25 degrees Celsius in which OH minus equals 2.1 times 10 to the negative 8 molarity is what? All right, so you're going to again take your negative log of your OH minus is the way I would do this. And so once you've taken your negative log of OH minus, you'll find it's a value somewhere around 8-ish, right? And so, let me go ahead and do that in my calculator. Right, if you take the negative log of this OH minus value, you're going to find that this POH would be 7.67 repeating. So, all right, so what you can do then is take 14 minus that value, and that will give you then your pH, which is 6.3. Now, oftentimes when I see these sort of problems and they have multiple choices, I would typically just take, okay, this is going to be something that's not quite going to be 8 because this is the value up here. We're taking a negative log. And then these have to add to 14, so it's not going to be that, but it's going to be something very close, right? Which is 6.3. However, to do it on the calculator, you of course take the negative log of this value here, and then you're going to take 14 minus that value. So the pH of a solution is raised from 3 to 5. Which of the following statements is false? Well, the pH decreases from 11 to 9. Of course, you just take 11 plus 3, 14, 9 plus 5, 14. That's true. H plus decreases by a factor of 20. Wait a second. These are times 10, right? Every time you do this. So changing to units would give you 100 times difference, not a factor of 20. And so that has to be the wrong one right there. All right, so when you're solving for pH, you should focus on the solution components and their chemistry. Determine the significant components, list the major species, and focus on those that furnish the H plus ions. Because again, you're solving for pH, right? The major species are going to be the solution components that are available in large amounts, which you probably could have figured out just from the name. All right, so the interactive example here that we're going to do, the pH of some strong acids. Let's calculate the pH of a 0.1 molarity HNO3, and we'll calculate the pH of 10 to the negative 10 molarity HCl. All right, so right here we have HNO3, that's a strong acid. The major species in solution will be your H+, your NO3-, that's the conjugate base, and the water, which is H2O. So the concentration of HNO3 is going to be virtually 0 because this is a strong acid. This should completely dissociate in water. The OH- will be very small because the H+ ions from the acid will drive the equilibrium far to the left. So when you're looking at this right here, that's your water autoionization, right? You would expect this to completely overwhelm that. So the acidic solution, where you have much, much more H+ than your OH-, so the OH- has to be much, much less than 10 to the negative 7 that would be in a neutral solution. And the sources of H+ will be, well, you have your H+ coming off of your nitric acid, which is HNO3. And that is 0.1 molarity, because that's going to completely dissociate, right? So we'll have 0.1 molarity of the H+ from that. We have some H+ from water, but that's going to be normally from the autoionization of water would be something like 10 to the negative 7, right? But that's really small compared to 0.1. That's something that if you added that, it would make no difference. So what we can do is we can just use the 0.1 molarity contribution from the HNO3, and we can just completely neglect the water here. And this is true anytime you have values that are typically larger than 10 to the negative 6-ish, okay? If you're 100 times difference, you can pretty much ignore water's autoionization, all right? So typically when you put in any significant concentration of an acid in, it will completely overwhelm the water. So, since the dissolved HNO3 is the only important part, you just put in that 0.1 molarity concentration of the HNO3 as your H+ concentration, because it will completely dissociate due to it being a strong acid. And what that means is you just take the negative log, defining the pH, and that will give you a pH of 1. Now, every time you do a problem like this, every time you do a chemistry problem, you should always double check and think, does this make sense? And so this is an acid in the solution. It's an acidic pH. Okay, that makes sense. All right, this right here, this part B, this is the reason you should always check if does this make sense. There's two ways you could try to do this. If you make the wrong deductions, if you don't understand what you're doing here, if you check and make sure your answer makes sense, you'll realize you messed up and you can go back and figure out why you did it. Now, in an aqueous solution of HCl, the major species would normally be H+, Cl-, and water. However, the HCl in the solution is so small, it just doesn't matter because you have 10 to the negative 14 of it. It's so small, it's completely a meaningless number. And so, it's not going to affect the autoionization of water, which is 10 to the negative 7, right? Or another way of saying that, it's going to be essentially pure water because you have so little HCl, it doesn't actually change it from being pure water. So it's going to end up being pH 7. Now, if you had tried to do this by taking the negative log of the concentration of HCl, you would have gotten a pH of 14. If you messed up and got a pH of 14, if you just sit there and go, hey, does that make sense? I added acid and it becomes basic, you would realize that that doesn't make sense really quickly, okay? So what are the major species in an aqueous solution of HCl again? Well, we have water, H+, and Cl-. So this is the problem solving for a weak acid equilibrium problems. You will notice they are very similar to the problem solving for any other equilibrium problem. They're just a little shorter and easier. So list the major species in the solution. Choose the species that can produce H+. Write that balanced equation for your reactions producing H+. By the way, you can just use HA if you want to for all of these. You don't actually have to write HCl, HF, H whatever. Use the values of the equilibrium constants for the reactions. Decide which equilibrium will dominate in producing H+. Write the equilibrium expression for the dominant equilibrium. List the initial concentrations of the species participating in the dominant equilibrium. Define the change needed to achieve equilibrium. Define X. Write the equilibrium concentrations in terms of X. Substitute the equilibrium concentrations into the equilibrium expression. Solve for X the easy way. So if you have a value that is minus X to a much larger initial concentration, you can just use that initial concentration just like before. You remember the 5% rule we talked about before? Well, same thing here. And then we can use the 5% rule to, of course, verify whether the approximation would be invalid. Then the last part is you're going to calculate the H+ and the pH of your values. So the hypochlorite ion, which is OCl-, is a strong oxidizing agent, often found in household bleaches and disinfectants. It is also the active ingredient that forms when swimming pool water is actually treated with chlorine. In addition to its oxidizing properties, hypochlorite ion has a relatively high affinity for protons, so it's a stronger base than Cl-, and which means that typically is going to be part of a weak acid, weak base system equilibrium that we've seen before. It also forms weakly acidic hypochlorous acid, which is this acid right here, HOCl, which has a Ka of 3.5 times 10 to the negative 8. So if you calculate the pH of 0.1 molarity aqueous solution of hypochlorous acid, that's going to be our problem right here, by the way, if you're wondering. Yes, there was a little bit of buildup for that one, wasn't there? All right, so by the way, one of the interesting things these are commonly used not just for bleaching pools and such. Some of the municipalities and still even in the U.S., will use hypochlorite ions as the disinfectant for your drinking water even. Very low concentrations, but still, that's not a great thing. So calculate the pH of 0.1 molarity aqueous solution of hypochlorous acid. So the first thing we need to figure out is we need to go ahead and figure out what our weak acid is. So HOCl is a weak acid. That means it's going to remain mostly undissociated. You're going to have HOCl that remains as HOCl in water. The major species thus will be HOCl solution, HOCl, and water. Those will be your two largest concentrations or largest amounts. Both species can produce H+. Both of these could act as acids. However, you know, because Ka is a fairly large value as compared to some of the others, that the HOCl is actually going to be what you're going to be concerned with as your acid. And so, you see here, this is the difference. Right here we have our HOCl. We see that its K is 3.5 times 10 to the negative 8. It's a much larger value for this acid dissociation. Versus water, which is 10 to the negative 14, which is a much smaller value. So this right here is our acid in this reaction. So we have HOCl. It is a much stronger acid than H2O. We can write this equilibrium expression right here, which is the equilibrium expression for that HOCl dissociating. This reaction right here. So again, products of reactants. By the way, feel free to just put HA, A minus, and H plus if you want on all your work. It doesn't matter. It'll work fine. Okay, so again, we end up with pretty much the same thing every single time we do one of these problems, by the way. H plus, conjugate base, and our weak acid right there. And this is going to have a Ka, which is 3.5 times 10 to the negative 8. And so our initial concentration for our HOCl, which is that bottom term, is 0.1 molarity. Our initial concentration of OCl minus is 0. We didn't have any of that. And the H plus concentration, technically it is 10 to the negative 7, right? That's the autoionization of water. However, you can save yourself some work. If you have such a large concentration here, we can just neglect this 10 to the negative 7 we would have had, okay? We can just set this to 0. So just ignore the autoionization if you have a fairly large concentration. All right, so the system will reach equilibrium by dissociating this HOCl. So again, we're going to do that same thing we did on all of our ice problems. We're going to let X be the amount of HCl that dissociates to reach equilibrium, or our change, right? And so again, that's our initial concentration minus our change, because we're using this up, we're disassociating this. So that will be 0.1 minus X. Our OCl minus started off as 0, and we're adding X. Notice these are always 1s because we're always doing it 1 proton at a time. And so this is going to be X. So anything we use of this has to make this one. And of course our H plus has to make the same amount. So if we substitute these concentrations into the equilibrium expression, this will give us this right here, which is our X squared over our 0.1 minus X, right? And if you wanted to do this problem, it would be a little bit on the harder side because again, you'd have to do your quadratic, right? However, Ka is a pretty small value here, isn't it? And so we could try to assume that this X down here, if we subtracted this very small value of X, it won't make any difference here. Which means we would just assume this would be 0.1. Or again, the concentration of our HA at equilibrium would essentially be the same as initially, that we wouldn't use enough for it to matter. And so we go ahead and solve the problem like this instead, which is our x squared over 0.1, which is the initial concentration. We've went ahead and just approximated that minus x on the bottom won't matter. Again, that's that plus minus. If you subtract or add a small number, it won't matter, right? And so we then solve for x. That will give us x equals 5.9 times 10 to the negative 5. All right, so the next thing we have to do is, because we made that assumption, we need to see if that's a valid assumption. So is that a small enough number that it doesn't affect this, that subtracting it wouldn't matter? And so this is the 5% test. We go ahead and take that x, we divide it by the initial concentration times 100, and we find out that's 0.059%. It really didn't matter at all. We're good. And so the next thing we do is we figure out the H plus concentration and our pH. Well, technically we've already figured out our H plus concentration, haven't we? Because H plus concentration was the same as X. And our value of X we already figured out as 5.9 times 10 to the negative 5. And that'll be molarity now, because that's concentration. And our pH is just going to be the negative log of this value. So we take the negative log of this value right here, and that'll give us 4.23. So what are the major species that are present in 0.250 molarity solutions of each of the following acids? So calculate the pH of these solutions. So our major species for this is going to be HNO2 and H2O. And our pH would be 2 in this case. So if we have 0.25 molarity of this, that would give us a pH of 2 here, because again, that is an acid. So right here, our major species will be acetic acid and our water. And again, what we're doing is we're looking these values of Ka up. We're doing the same problem we did in that previous exercise example I just went through with you. And we're just figuring out based on this acid right here, which has our Ka value. And that's what we're doing for both of those, okay? This is just extra exercise you guys don't really need because you have OWL to work with, but I still leave them in. Calculate the pH of a solution that contains 1 molarity of HCN. Ka is 6.2 times 10 to the negative 10. And 5 molarity of HNO2, which the Ka equals 4.0 times 10 to the negative 4. Also calculate the concentration of cyanide ion, Cn minus, in this solution at equilibrium. So we have HCN and we have HNO2 here. So our HCN and HNO2, these are both weak acids. And so they're largely going to be undissociated. The major species in the solution will thus be HCN, HNO2, and water. So all three of these components could produce H+, and do produce some H+. So our HCN, this is going to be this acid right here, and that's our H+, conjugate base, and our Ka is right there for it. Here's our HNO2, and you can see the Ka is much, much larger. And right here is our water, which the Ka is incredibly small, almost a meaningless amount, right? In fact, you could say it's a meaningless amount. A mixture of these three acids might lead to actually a very complicated problem if their Ka's were close enough. However, and by the way, if you ever want to figure out how to do that, you can join me in an analytical chemistry class someday. However, the situation is greatly simplified. Even though the NO2 is a weak acid, it's so much stronger than the other two that we're talking tens of thousands of times stronger. See, 4 units would be a 10,000 time difference in concentration. So the concentrations off of this will be so much more than these two that really you don't have to do these other two. You can just ignore them. And thus we can take the HNO2, and that'll be the dominant producer of H+. We can figure out the H+ from that. So we take the HNO2, and again, that's the H plus and NO2 minus equals the Ka. We again are going to take the initial concentrations minus the change. And of course, whatever we use of this has to produce these two. And so, yes, whatever we use right here, it produces these two values. Notice this approximately 0. Again, we are ignoring the fact that the other two produce H plus because they're just so small it won't matter. Here's our ICE table. I have it in ICE table format even, which is quite nice, right? We have our initial value of our acid here minus the change, and that will give us our equilibrium value. And of course, our equilibrium value for these two are x's for each of these. All right, so we'll go ahead and substitute those in our equilibrium expression. Again, notice that this, again, is a much smaller value than 5, right? And so 5, we can just take and get rid of this minus x down here and just use 5. We can just make the 5% rule assumption. So our x squared will again be over 5. We go ahead and solve for this, and which is this 4.0 times 10 to the negative 4 times 5, and then take the square root. And then we are going to get this value of x right here, which is 4.5 times 10 to the negative 2. You can see that that value is considerably smaller than 5. And right here we see that it's a 0.9% difference, which is not significant. Okay, so we have our x. Now remember, our H plus concentration is the same as that x. And so that is 4.5 times 10 to the negative 2 molarity. Our pH is just the negative log of this value right here. So we take the negative log of this value, and we get a pH of 1.35. This is an acid, so that makes sense. Okay, so the next thing we need to do is we need to figure out our equilibrium concentration of the cyanide ion. How can we do that? We skipped that problem, didn't we? Well, we made the problem easier now. We have the H plus concentration. Well, that's one of the equilibrium components here, isn't it? So, remember this equilibrium right here. The cyanide ions in solution. This comes from this dissociation right here, right? Which one of the components is H plus. And so, although the position lies far to the left and we do not contribute significantly to the H plus, the only source of Cn minus is that HCN. So even if that's a small number, that's the only source. That's the only thing we're getting for Cn minus, okay? We have to use that. So again, we're going to take our equilibrium expression, which we have right here. And again, we see that this equilibrium expression, this is that same thing again, right? H plus, Cn minus, and HCN, all to the first power. Again, these are going to be the initial concentration minus change. This right here, we know this term, don't we? Because we have already calculated the major source of H plus. We can just put that in now. And so we've actually created a somewhat simpler problem. So we take that H plus concentration that we figured out before, okay? It doesn't matter where the H plus comes from, because H plus is H plus no matter its source, right? That's what we know from the law of multiple proportion, from way, way at the beginning of General Chemistry 1. That's what that sort of, that's one of the key factors of the information you learn there. Now, the equilibrium H plus, we can just insert that equilibrium H plus that we figured out before, which is 4.5 times to the negative 2. So, the only thing we now need to figure out is what is the HCN at equilibrium? Well, we know the initial amount is 1. The Ka is incredibly small. And so, any amount that we dissociate is going to be negligible. And that means we can go ahead and just plug in that initial concentration of HCN as our equilibrium concentration. And so now we have two numbers that we didn't have to figure out, do we? All we now have to figure out is a single value, which is that Cn minus concentration. Again, we get this from the previous problem, the H plus concentration of the entire mixture, which we figured out in that previous ice problem. This right here is again the initial concentration because that minus x won't matter. We can ignore that. And so we take these values, this divided by 1, which is self. We're then going to divide 6.2 times 10 to the negative 10 by this number right here, 4.5 times 10 to the negative 2. And that will give us our CN minus concentration, which you'll notice is very, very low. 1.4 times 10 to the negative 8. All right, so since that CN minus only comes from that HCN, that's the only source, that means only 1.4 times 10 to the negative 8 moles per liter of that HCN dissociated. That's almost nothing, isn't it? It's a very, very small amount compared to 1 molarity, right? So that's a very small amount. Our expectation that this was a very small amount from our Ka value, that was true. We made a good assumption before. Excellent. Great job. All right, so the next thing we're going to introduce here is percent dissociation. So percent dissociation is the amount dissociated divided by the initial concentration times 100%. For a solution of any weak acid, HA is going to be the H plus will increase as the HA decreases. The percent dissociation is going to increase as the HA decreases. So let's try calculating this percent dissociation for an acetic acid problem here. And so acetic acid has this Ka right here. It has a 1 molarity concentration of acetic acid as our initial concentration. So again, acetic acid is a weak acid. Our major species are going to be the acetic acid, which is this, and water. So acetic acid is stronger than water though. So right there's the acetic acid equilibrium, and it is going to H plus and its conjugate base. This is going to be the most important one. We can ignore the one for water here. And there's our Ka for acetic acid and our equilibrium expression, which hopefully by now you have pretty much down pat because it's the simplest Ka of all the ones I've shown you so far, which is they're always the same. H plus, conjugate base, and there's your weak acid on the bottom, right? And they're all to the power of 1. All right, so again, we have an initial concentration again. We have a change in concentration. We're going to do the same thing over. And this is one of the reasons why these ice problems get kind of exhausting and boring, because they are pretty much the same problems over and over and over and over, just with different species. All right, so again, we have our equilibrium concentration. It's going to be the initial minus change. Anything we use up for the acid, we'll make H plus and our conjugate base, that amount. All right, so again, our concentration right here, our initial concentration, is much larger than our Ka would indicate we would make, right? Or use up, consume in this case. And so what we see is, again, we can go ahead and assume that this minus x here won't matter. So we go ahead and get rid of that. We have x squared over 1. And so it's 1.8 times 10 to the negative 5 equals x squared over 1. We go ahead and solve that, and we find out that value for x will be 4.2 times 10 to the negative 3. We go ahead and do the 5% rule to see if that is true, and we find that that is valid by the 5% rule. That's fine. Again, if it's 100 times difference from this, you know that's fine. That's what that is, right? Right here you have x again. We figured that out. That's again going to be the concentration of H plus. So we already have our value. There you go. That's the concentration of H plus. All right, now we have the concentration of H plus at this point. Now we need to get the percent dissociation. And so what it's going to be is literally it's the amount that dissociated. Now, the formula that you're going to keep seeing, because we're typically working problems where this is the acid that gave up H pluses, this you typically is what you're going to see, is the H plus concentration over the initial concentration of your acid. And usually that will work, okay? And that's because usually this is the acid that's giving off H plus, which, H plus will equal the amount that's left over. Interestingly enough, the actual formula is the conjugate base divided by the initial amount of that acid. So if this is not the acid that's giving off H plus, this formula will actually break. So be careful. Use the original formula, which is way up here. I know by the time we do this stuff, you guys typically forget the original formula for it. Whoops, went too far. Excuse me. Okay, so this is the original formula. Remember, it's the amount dissociated. So if we're talking about HA, this would be A minus over the initial concentration of the HA. When we're talking about this right here, technically this value up here should, yes, be C2H3O2 minus. But since we calculated the H plus and it's going to be the same as that value, they were both X, we can use this as a shortcut. We can just plug that in. Okay? That's one of the things people get confused of on these problems. All right, so again, that's going to be that value of X for the amount of the conjugate base divided by the initial concentration of our acid times 100 to make it percent. What we find out is it's 4.2 times 10 to the negative 3, which is what we found out for that X value. Divide by 1 times 100% for a 0.42%. All right, so let's use the Chatelier's principle to explain why percent dissociation increases as the concentration of a weak acid decreases. So dilution shifts equilibrium to the side with the greater number of particles. So percent dissociation will increase. That is the reason why the Chatelier's principle works on these, okay? If you're wondering how this relates to the previous equilibrium information you were given. All right, so let's try another interactive example. Lactic acid here is a chemical that accumulates in muscle tissue during exertion. You probably already knew that, actually. 0.1 molarity aqueous solution, lactic acid, is 3.7% dissociated. So let's calculate the value of Ka for this acid. So in this case, we're going backwards. We actually know how much is dissociated. We know the initial concentration. We need the Ka for this. And so what we're going to do is, again, our major species is going to be this lactic acid and water. In this case, even though the lactic acid is a weak acid, it's going to be the more important one than water. And typically that is true unless you have very, very small concentrations or a very unusual, not really a weak acid, quotation marks around it, weak acid, okay? Meaning, if I give you something that's a weaker acid than water, that isn't really a weak acid. That's by definition. Now, the dissociation reaction will be this. This is the lactic acid dissociating. Again, how do you know that? Well, it gives up an H+, right? That's what acids do. So your equilibrium expression will again be the same sort of thing. Your acid and your conjugate base on top with H+ right there. Okay, now, we have the initial concentration as lactic acid. These other two did not have any. We're going to assume that the water amount of H+, the autoionization, will not be significant. And so again, we have that equilibrium concentrations, which are 0.1, the initial, minus the change, right? And then these will be equal to that amount of change. So whatever you use here has to show up here. All right, so this equilibrium amount, these can actually be obtained from our equation for our percent dissociations. So we actually were given a percent dissociation this time. So we know 3.7% has to equal this x, this change, divided by our initial concentration times 100%. So we divide over 100 over here. We multiply over 0.1, that's that 0.1 right there, right? And that will give us our x. And we go ahead and do the work. 3.7 times 10 to the negative 3 moles per liter. That's going to be our x, our change in our concentrations. And so we can calculate these out. We go ahead and minus x, we minus that value. We would end up just rounding it right back up because, it won't matter. That's the correct significant figure, so it's such a small value, it doesn't change anything. Our concentrations, however, of our conjugate base and our H plus will both equal that x, which is 3.7 times 10 to the negative 3. So we go ahead and plug these into our equilibrium expression. So there's our x, and our initial concentration down here because it didn't change when we subtracted that x off. And we plug these in, we do the math, so multiply these, divide by 0.1, and we get a Ka of 1.4 times 10 to the negative 4th. And that's it. That was the answer to the problem. All right, so this is the problem solving for acid-base problems. So again, major species, look for the reaction that can be assumed to go to completion, if then you can. For a reaction that can be assumed to go to completion, determine the concentration of your products. Write down the major species in solution after the reaction. Look at each major component of the solution and decide if it is an acid or a base. Pick the equilibrium that will control the pH. Use known values of the dissociation constants for the various species to help decide on the dominant equilibrium. Write the equation for the reaction and the equilibrium expression. Compute the initial, this is just the same sort of stuff you saw before, really. Really, this is the same problem. The only step here that's really different is you're subtracting off any base from the acid or acid from the base, and you'll see in this problem right here. All right, so that's your exercise. So when you do these problems, this is the major place that differs. Okay, remember that. The acid-base problems. Essentially, you have to look at the acid-base will react first, and then you look at your normal dissociation. Okay. Another way of looking at it is you're removing some of the H plus if you put base in, right? And that's what you figure out first. Okay, so let's go ahead and do a few join-ins real quick. I'll have some exercises a little bit later as well. So what are the major species in an aqueous solution of HF? So the Ka value for HF is this value right here. And so what we're looking for is, this is a weak acid here. So our major species in solution are going to be our water and our HF. Those are the ones that we'll have the most of. By the way, in an aqueous solution, water is always a major species because it is the single largest component. All right. Which of the following graphs best represents a plot of H plus versus the initial concentration for an aqueous weak acid at constant temperature? Well, that would be B. It's a logarithmic scale. So again, the concentration of your weak acid is going to be a logarithmic input. All right, so the percent ionization for a 4 molarity weak acid, HA, is blank. The percent ionization for an 8 molarity weak acid, HA, is blank. So you would expect here that the 8 molarity would have a larger percent ionization than, the 4 molarity would have a larger than the 8 molarity. What this is, again, this is a logarithmic scale. And so your 4 has a lower denominator than 8, which is a larger denominator, and thus going to give you a greater percent ionization than the 8 molarity. The pH for 4 molarity weak acid, HA, is blank than the pH for the 8 molarity weak acid, HA. And so you would, again, all right, I had to look and see where I am. Again, this is a case of where you have 4 molarity. This is a lower concentration here. The pH for the 8 molarity weak acid, excuse me. Okay, so remember that as you add more acid, it becomes more acidic, right? The more acidic something is, the lower its pH. So pH, this number pH will be larger than the pH for this 8 molarity weak acid here. Remember, this will be a less acidic, more basic solution here. This will be more acidic, lower pH here. All right, so strong bases are similar to strong acids. They're just the basic form. And so this will be completely dissociated in water. The examples that you should have in the back of your head for a strong base are going to be the hydroxides of the group 1A elements. That means the first column on the periodic table combined with an OH. Another one are the alkaline earth hydroxides, which is group 2A, combined with an OH. This will have, of course, 2 OHs, so I'll have little parentheses around it and a 2. All right, so this is an example of that second case of a base, which is the alkaline earth metal with the OH. This is slake lime. This possesses low solubility, which is actually where you get the slaked from. When you mix it in with water, a lot of it will still be insoluble. And so it will not all be dissolved in solution. You get slake, which is a sort of like a slurry. This is used for scrubbing stacks of gases to remove the sulfur dioxide and keep coal from producing sulfuric acid rain. This is used in water treatment plants. The lime soda process, which is lime, calcium oxide, and soda ash, which is sodium carbonate, are added to hard water in order to soften it. So let's calculate the pH of a 5 times 10 to the negative 2 molarity NaOH solution. This is a strong base, and so our major species that we have to be concerned of are those the NaOH, which is, when dissolved, is OH minus ions in solution. And so our solution, when it comes down to it, is just going to be the concentration of that NaOH solution, which we are given right here. That is going to be our OH minus concentration in solution, because this is a strong base. It completely dissociates, completely comes apart. And so our concentration for the H plus can be done using the Kw. So we take Kw, which is 10 to the negative 14, we divide it by our OH minus concentration, which is displayed right here, and that will give us our H plus concentration. And if we were to go ahead and do the pH for this, that would be 10 to the negative log of this value right here, which would give you a pH of 12.7. This is, of course, a basic solution, which hopefully you would expect considering we are talking about adding a base to it. All right, so the added OH minus from the our salt, which is NaOH, has actually shifted the water autoionization equilibrium to the left. This will significantly lower the H plus compared to that with pure water. And so again, we've added a bunch of this, right? And the Chatelier's principle says that this should be shifted to the left, which it did, lowering this H plus concentration. So When bases react with water, they increase the concentration of hydroxide ion. They can have at least one unshared pair of electron that is capable of forming a bond with a proton. Some of these examples are going to be methylamine, dimethylamine, and pyridine. These are all examples of Bronsted-Lowry bases that will cause a buildup of OH when you introduce them into water, which also fulfills the definition of an Arrhenius base. So this is your general reaction between a base and water. And so right here we represent the base by just writing B. And we represent water here, which is our acid, by of course water. Now water will donate an H plus to the base. And so our conjugate acid will be BH plus. And of course that's our base that went ahead and got an acid, right? Went ahead and got an H plus, excuse me. And right here, this will be our conjugate base, which is OH minus. That's the conjugate base of water. And so our equilibrium constant for these is going to be Kb equals BH plus, which is our conjugate acid, and then OH minus, our conjugate base, over B, the concentration of our base. Remember, water always gets left out because it is a pure liquid. So Kb, this is going to refer to the reaction of a base with water to form the conjugate acid and the hydroxide ion. With weak bases, the Kb values are going to be small. With strong bases, these are going to be larger and larger. Now, a strong base and a strong acid, their Kas and Kbs, are actually usually listed as being infinite or just very large. They don't actually usually have numbers because they run to completion. But the larger the Kb value, the stronger the base. The lower the Kb value, the weaker the base. So let's calculate the pH of a 1 molarity solution of methylamine. And its Kb is this value right here. So methylamine, this is a weak base. Our major species, again, are going to be that methylamine water. In this case, we have a pretty significant concentration of that. And its Kb is pretty, moderately large. And so water is not going to be our big species that's going to, its autoionization is not going to be what we have to deal with. What we have to deal with here is going to be the reaction between our base and water. And so we go and write out that same reaction we looked at before. This time it's just methylamine here. And so we can generate our Kb from this. Again, it is our conjugate acid right here, conjugate base, and our base right there. This right here is the Kb we were given. On homeworks, typically you may have to look this up for some experience using your textbook. But in general, in exams, you're going to be given these values if you're expected to find things like pH, concentrations, that sort of thing. If you're not given it, then you're probably finding it. All right, so this is the ice problem right here. This is again going to be initial change equilibrium. Our initial concentration was given to us. It's going to change by minus x. So it'll be our equilibrium value of 1 minus x. Again, this does not matter because this is a pure liquid, not included in the equilibrium expression. We don't care. And honestly, there's so much of it we won't be able to majorly change it. This right here, again, whatever we produce is going to have to come from this. So these are going to be both x. Now, a note, by the way, that yes, we have assumed that OH minus is just being produced by this. We went ahead and just assumed that that amount, that 10 to the negative 7th or whatever, from autoionization won't significantly contribute here. So we will go ahead and use our normal approximations. Again, that Kb in this case is fairly small. And so we can go ahead and just get rid of this minus x right here and put in our initial concentration instead. So again, we use our x squared over 1, and that will equal our Kb. By the way, be careful. You need to always use Kb's for these problems. A Ka will not work properly. This is not a Ka, okay? It's for a base. All right, so when we solve for x here, we get 2.1 times 10 to the negative 2. If we go ahead and plug that back in to see if our 5% rule works, it does. It's fine. And so this x value, well, that's our concentration over OH minus, isn't it? So if we get our POH, that's going to be 1.68. Again, how do you get that? Well, you take the negative log of this value. That's your POH. How can you get pH from that? Well, 14 minus the POH will give you the pH, which is 12.32. Now, this was a problem for a base. We would expect the pH to be basic, and it is, which is good. That's a great sign. All right, so let's consider two separate solutions for equal concentration. The first solution contains sodium hydroxide, and the second solution contains barium hydroxide. Which of the following statements will be true? The sodium hydroxide solution has the lower pH. The barium hydroxide solution has the lower pH. The pH of values of both solutions are equal. Well, this is going to be the sodium hydroxide solution will have the lower pH. Why would that be? Well, okay, so remember again, you're adding bases here, okay? And so this is a base, this is also a base. These are both strong bases, in fact. If you looked at your periodic table, you'd see those are groups 1 and 2. Now, the sodium hydroxide, though, is only going to have one OH per sodium. The barium hydroxide is going to have 2. And so that has more OH minus ions. That means that this is going to be more basic, whereas the sodium is going to be less basic. It'll be more acidic. And so you would expect the sodium hydroxide solution to have the lower pH, which is the more acidic pH. What volume of water must be added to 100 milliliters of aqueous NaOH solution to change the pH from 12 to 11? Okay, again, don't forget that every pH unit is a factor of 10 change. So we're starting off with 100 milliliters. We need to get the total volume up to 1,000. Again, that's the total volume though, right? If you have 100 milliliters, to get to the total volume of 1,000, you need to add 900 milliliters. All right, so we've been doing monoprotic so far. Let's go ahead and talk about some polyprotic acid, which means multiple protons that they can donate. So some acids can furnish more than one proton, of course. There's the diprotic and triprotic acids. You're always going to look at these by dissociating one proton at a time. So the conjugate base of the first dissociation equilibrium will actually become the acid in the next dissociation. Okay, so just remember, it's always easier to take chemistry step by step. It's actually one of the beautiful things about science, is it allows you to take massive problems that are just unsolvable by any single one person and break them into pieces and solve them in small, tiny steps that then anybody can use and solve. So, triprotic acid. This has the ability to furnish 3 protons. That's where the tri comes from. Phosphoric acid is probably the best example, and kind of a great example because this is a common preservative they use in a lot of drinks. So, for the typical weak polyprotic acid, and really for any polyprotic acid, I've never seen one this is not true actually. So this would have to be an extremely unusual case. The first proton that comes off is going to be your largest Ka. That's going to be the easiest one to remove. The second proton that comes off, that's going to be much harder. And so your second Ka is usually much smaller than that, significantly so. And then if you have a third proton to come off, that's usually going to be even smaller. And so one of the easy way to remember this, and it kind of makes sense if you think about it this way, is that every time you're removing a proton, you're becoming more negatively charged, right? Which means you're more attractive to protons. So typically Ka1, that's the first proton coming off, by far and away the biggest one. If it's going to be a strong acid, this is going to be where it's going to be a strong acid. Ka2, if it has it, this is much smaller, okay? And so on. So when you do these problems, typically because the Ka1 is usually a lot larger than the Ka2 and 3, only the first proton that comes off for most polyprotic acids will actually determine your H plus concentration. The rest of the protons that come off usually don't have any significant effect because those Kas are so small that the amount of, they're just not very strong acids. They're usually at that point quite weak actually in terms of acidity. So let's calculate the pH, excuse me, of 5 molarity H3PO4. Now here what we're seeing is this is a triprotic acid. Again, that's the 3 protons right there. And let's go ahead and get the equilibrium concentrations of the species. So we have the H3PO4, so what's remaining from our initial amount we put in. Our H2PO4, that's the one that lost a proton. Then the HPO4, which has lost 2 protons at this point. This is going to be, so this is your first acid. This is the conjugate base of that acid. This then will be your next deprotonation. This will be the acid of that one, your Ka2, going to this. Then finally, you're going to have your third deprotonation, your third giving up of an H+, which is going to be HPO4 to PO4. By the way, if you ever wonder why I rephrase it in layman terms, I'm trying to help people that still maybe don't have the vocabulary quite to the point yet. Anyways, these are your 4 species of this H3PO4. Each of them is an acid-base pair every time. So the major species in solution are going to be your H3PO4, excuse me, and your water. And of course, these are going to act as your acid and base, right? So your water, you're so used to probably now water acting as your base. Yeah, that's going to be true here too. None of the dissociation products of the H3PO4 needs to be written, since your Ka values for all of them are so small that they're going to be minor species. You don't have to worry about those for this first part. So the dominant equilibrium in your dissociation of H3PO4 is just going to be your normal acid-base equilibrium right here. So right here you have that normal acid dissociation equilibrium, right? Giving up an H+. That's going to have that same acid dissociation constant and expression just like all the other ones, right? Again, you're donating a proton. Okay, so we're going to go ahead and do the exact same thing again. We'll set up our ice table. We start with our initial concentration of 5. We're going to change it, so we're going to use up some amount of that, which gives us 5 minus x. Again, this x is going to be so small that we can go ahead and just, use 5. Right here, we're going to have, well, we only make this amount that we use up here, and so that's going to be x. This right here is going to be x because that's all we're going to make. And so what we're going to do then is we're going to substitute those equilibrium concentrations into our problem again, just like before. And we make that same assumption again because it's going to be a good assumption. As long as this Ka value is significantly smaller every time. And so we go ahead and solve for x. We get x equals 1.9 times 10 to the negative 1. So our x here is 1.9 times 10 to the negative 1. If we go ahead and plug that in, figure out if it's 5% or less of 5, it is. It's less than 5%. And so that was a good assumption that works. And that means that our H plus concentration is going to be that concentration of 0.19. And our pH is going to be, well, the negative log of that value. And so 0.72. All right, so the next part, we have to figure out our equilibrium concentrations of the other PO4 species, right? of that HPO4, PO4, and H2PO4. We've already figured out more or less the H2PO4 concentration here, but let's go ahead and talk about it a little bit. So we figured out that that X was 0.19, right? And that means that that's going to be the concentration of our H2PO4 as well, because for every H plus we also make one of these. Now, our H3PO4, its concentration is actually going to be the initial minus that change, right? That X, which is that 0.19. And so if you go ahead and plug that in, it is enough of a change that we can go ahead and reflect it in our values here. So it is 4.8. Great. Now our concentration of HPO4, this can be obtained using our second deprotonation, our Ka2. And so we go ahead and put Ka2, we get our value and put it in here. And then this is going to be this same expression we see all the time here, which is H plus concentration times the conjugate base, which is HPO4 2 minus in this case, which is right there. The acid form, which is going to have the extra H plus. You'll notice I've actually dropped a charge here. Sorry about that. Anyways, it's still the H2PO4. You can get it. It has it correct over here. Okay, so these H plus concentrations and the H2PO4 concentrations, we already figured those out. And they're not going to change significantly from that tiny little Ka right there. So we can just go ahead and plug those values in. And that makes this problem extremely trivial to solve. So we plug these values in, 0.19 in each of these places. Well, 0.19 divided by 0.19 is the same value. So they're going to cancel. And that means these two cancel right here, right? And that leaves you with this equals what you're trying to find. Ta-da! Which is very nice, right? Again, like I said before, the more information you have, the easier these problems become. They actually significantly become almost a joke in math, right? Where you almost have to do nothing. As long as you understand acid-base vocabulary, terminology, and the ideas behind it. So let's calculate the PO4 3 minus. We can use the expression for the Ka3. In this case, we now have the H plus, we had that before, and we have the HPO4 2 minus as well, which we just figured out. And so we again create our expression, H plus, PO4 3 minus this time, and then our previous, which becomes our new acid here, which is HPO4 2 minus. So we're going to go ahead and plug these values in. Our H plus is 0.19, just like before. And this HPO4 2 minus is this value right here, which is the 6.2 times 10 to the negative 8. Remember, this again comes from our previous problem, our table. And so we go ahead and solve for this value right here, which is the PO4 3 minus concentration. And we get this value right here, which is 1.9 times 10 to the negative 19 molarity. Notice this value is, these values are getting incredibly small, aren't they? And that's why we could make that assumption that the H plus just depends on the first deprotonation, because these values get very, very small very quickly. All right, so these results actually show and prove that they don't make important contributions to the H plus. They just don't matter in terms of H plus concentration. All right. Okay, so sulfuric acid is a unique one. It's a unique polyprotic acid. It's an example of an exclusion. That means that all the other ones, almost every other polyprotic acid will follow that previous pattern, okay? It's only this one that you start diverging enough that matters. So it's going to be a strong acid in the first dissociation step right here. And that means the Ka is essentially infinite. It completely dissociates. So we have a one-sided arrow here. The second step is a weak acid right here. But it's actually a fairly strong weak acid as weak acids go. I mean, it's not a strong acid, but it is a stronger weak acid. And so, let's go ahead and calculate the pH of a 1 times 10 to the negative 2 molarity H2SO4 solution. You notice there's a reason I've done this 10 to the negative second molarity solution here. This number is pretty close to this one right here. And so we're going to have to start worrying about this second deprotonation now, aren't we? So we finally get to do a 2 deprotonation problem. And by the way, if you ever took analytical chemistry in the future, one of the chapters there, you have to do 10, 10 different species in the same solution. And this is actually pretty much how you do it. It really isn't that hard as long as you take it step by step, okay? But if you try to do it all at once, it will become very difficult. So, the major species in solution are going to be H+, our HSO4-, and our H2O. Notice the H2SO4 is completely dissociated. We don't have to worry about it anymore. So we can go ahead and just start with our HSO4-. Why is that? Well, again, our H2SO4 is completely dissociated. That means it's completely in the form of the H+ and the HSO4-. And so that means we start with initial concentrations, which is the initial concentration we were given, 0.01, or 10 to the negative 2, right? And right here, the H+ also starts with the initial concentration of 0.01 again, because again, these are the two products from that complete dissociation. And so we have then our change. Well, we use this up to make these, because we don't have any SO4- yet. All right, now, again, that's going to give us 0.01 minus x, 0.01 plus x, and then x for our SO4-. So let's go ahead and substitute these equilibrium concentrations into our Ka2 expression. So again, we have our Ka2, that's the value we're given. And we have 0.01 x plus x on the top times x here. We have 0.01 minus x here on the bottom. So what happens if we go ahead and make that approximation we've done before? So if we make that approximation we've done before, we would go ahead and get rid of the plus x and the minus x, because the addition-subtraction part won't matter. And so we would get an approximate value of this, which is 0.01 over 0.01 times x, which means the Ka would equal the x. Okay, so would that work though? That would give us an x value of 0.012. Wait a second. We're starting with 0.01, aren't we? Can we use more than what we start with? We can't, can we? This can't be a negative value down here. We can't use all of the concentration plus some, okay? And so that is a clearly ridiculous result. That doesn't make any dang sense. This is a case where you really just can't make that assumption. And so we can't use that regular assumption. We're going to have to solve this using the quadratic equation. So we go ahead and take our values here. We solve them out like so. We get them all on one side to set them equal to 0. We then plug in these values, this 1a, this a right there, which is 1 because it's blank, b, and c into our quadratic equation, a, b, c. And so the quadratic formula will give us one negative root. This can't be correct. We can't have a negative value. And so we have to take the positive root, which is that. So 4.5 times 10 to the negative 3. And there's your quadratic equation, by the way. I finally gave it to you. If you didn't look it up on, the internet, because we're all hooked up right now. All right. Anyways, there's your quadratic equation if you didn't already get it. So our H plus concentration is going to be, well, our initial value plus whatever we made, right? Which is that X. And so we add that in and we find out that our H plus concentration is 0.0145. We take the negative log of that and we find out the pH would be 1.84. So we see that the second dissociation in this step, this time in sulfuric acid's case, actually gives us almost half of the H plus we would get in the total solution. So we really can't do this by making successive approximations. We can only do this by doing this problem one dissociation at a time. Okay. Now, the conjugate acid and conjugate base of bicarbonate ion are what, respectively? So here we have bicarbonate. Right here, we can see that if it's the conjugate base, that's going to mean that it has lost an H plus, right? And so we lose a positive charge. It's going to be a negative 2 charge here. We lose an H. That'll be CO3 2 minus, just like that. Okay, so what would be the conjugate acid? Well, we're going to have an H plus gained, right? And so we're going to have 2 hydrogens, and that negative charge will be gone. And so that will give us that one right there, H2CO3. So, salts are another name for ionic compounds. This is one of the reasons why I may have confused you guys whenever I said ionic compounds and then salts and use those interchangeably. Hopefully you picked that up. If you didn't, well, now I explained it. So now I can use it and you can't be confused anymore, right? Anyways, disintegration into ions when dissolved in water, that's one of the key factors that determines if something's a salt, an ionic compound. That's one of those things that you were presented way back in Gen Chem 1, probably. Hopefully you were presented that actually before that. These have independent movement in dilute solutions, which means that dilute solutions have very low concentrations, right? And so in a dilute solution, typically the individual ions, the cation and the anion, they don't interact in solution. These can behave as acids or bases under certain conditions. And that's why they're getting brought up right here. So the salts that produce neutral solutions. When dissolved in water, the salts that consist of cations, of strong bases, and the anions of strong acids. For example, KCl, NaCl, sodium nitrate, potassium nitrate, right here. These are the components of a strong base. That's the cation of a strong base. That right there is the anion of a strong acid, HCl, right? And so these have negligible acidic and basic properties. And that means they don't have any effect on the H+, okay? So these will give you neutral solutions. So salt water, NaCl, and water actually gives you a neutral solution. That's not why the ocean's basic, by the way. I sometimes get that question. No. It's actually carbonates are the major reason for those water bodies being basic. And actually the reason for our blood being basic as well. It's very similar. So a basic solution will be formed if the anion of the salt is the conjugate base of a weak acid. So if it's something like acetate, okay, acetate is the conjugate base of acetic acid. So sodium acetate would give you a basic solution. The Kb value for the anion can actually be obtained from this relationship right here. Okay, I want you to step back for a second, kind of let yourself breathe, because this is one of the most common mistake places that even if I get really tired, if I don't have any sleep for an extended period of time or something, I can actually make this mistake myself. And it's a stupid mistake to make. But notice that the acids and bases, you've probably been thinking and dealing with the fact that these are like opposites, right? but they're not really, okay? An acid and a base are all reacting through water. They're not like the reverse of a equilibrium. So one of the things I commonly see people get mistaken on is they think that when you go from an acid, a Ka, to a Kb, it should just be the inverse. 1 over Ka should be Kb. And if an acid and a base reaction were just a reverse of themselves in equilibrium, if you didn't have water, then yeah, that would actually make sense. But all of these acids and bases are going through water, okay? And what that means is they all have to react through water. And so it is never just the inverse. It's always Kw divided by Ka equals Kb. If you wanted Ka, then you'd just go, well, Ka equals Kw divided by Kb. And remember, the key way you can remember this is all acid-base reactions go through water, okay? Which is Kw, water, right? Okay, so anyways, this right here is the conjugate base of a weak acid. It is, of course, a base. That's why it's called a conjugate base. And so, yes, that is a base. It will be basic. Yes. Okay, so let's calculate the pH of a 0.3 molarity NaF solution. Notice NaF, fluoride, this is a conjugate base of a weak acid. And so HF would have been the weak acid for fluoride. And that has a Ka value of 7.2 times 10 to the negative 4. So we're going to go, first thing we need to realize is this is a base problem, right? We're dealing with a base here. And that means we're going to have to convert this Ka to a Kb. That means taking the Kw divided by this number right here. Okay, so let's go ahead and look at our major species again. We have sodium, we have fluoride. Because this is a salt, it's going to dissociate in solution. Our F minus, this is a weak base. It's the conjugate base of a weak acid. Our H2O is also a major species, so we're going to be reacting our base, F minus, with H2O, which is going to be our acid. Notice sodium is actually like sodium hydroxide, would have been a strong base. So sodium has negligible acidic basic properties. It just doesn't matter. Okay, so our dominant reaction is going to have to be the F minus reacting with H2O, that's our acid, that's our base, forming the weak acid HF and OH minus. This is going to be yielding this Kb expression. By the way, one of the things you can help yourself remembering that the Ka and Kb are not just reverse flipped equilibria, is that this has OH minus in it. The acid one would have had H plus, right? And so they're actually completely different reactions that have different compounds in them and everything. It's just that, you know, these two chapters bump into each other and yeah, it happens. So, now, our Kb here, we're going to have to figure that out from our Ka. And so we're going to take the Kw divided by the Ka we were given for HF, and that's going to give us our Kb right here. Now again, we go ahead and do an ICE table just so we can organize everything. So we start with 0.3 molarity of the F minus. We don't start with any HF, and we go ahead and assume we don't start with any OH minus, because there's going to be 10 to the negative 7, that's just not enough to matter. At least we hope. And so, here we have 0.3. Well, we're going to have to use up some of this 0.3, so 0.3 minus x. That's going to give us x HF and x OH minus. Okay, so the next part we do is we go ahead and substitute those in just like we've done every time before. Just this time we're using a Kb, right? This time it's a base. That's the big difference. All right, so we substitute everything in, x, 0.3 minus x. Again, we see this is 0.3. This is a very small number. We could go ahead and assume that's just 0.3 in the bottom, right? We can always test later. Let's try to make the math easy. So we solve for x then. 2.0 times 10 to the negative 6. We try the approximation, and we find out that that's valid with the 5% rule. So it's 5%, it's less than 5% of this value right here. And so that's fine. That means our OH minus concentration would be 2 times 10 to the negative 6. The pH would just be the negative log of that value, so 5.69. To get the pH, I would take the 14 minus that 5.69 pOH value, and that would give you 8.31 pH. By the way, pH is the unit of these, if you're curious. This solution is, of course, basic. Thank goodness. If it wasn't basic, we'd be really mind tripping here and having some issues because we added a base. Should be basic. All right, so let's consider this dissociation of hydrocyanic acid. So right here we have hydrocyanic acid, and it, of course, is reacting with water to form the H plus and cyanide. So Cn minus appears to be a strong base in this reaction because this is a very, very small Ka, right? And so if we look at its Kb, it's actually quite a bit stronger as a base, isn't it? However, if we look at the other way, so let's think about this a little bit, okay? Right here, this is a very, very weak acid as far as you've seen. This is one of the smallest numbers you've probably seen in this chapter. And so, yes, it is a very weak base. But that doesn't necessarily mean that this is a strong... this is a very weak acid. I'm sorry, I think I said base. That doesn't mean that this is a strong base. Yeah, it's a stronger base, but that doesn't mean a strong base. It has a very special connotation, okay? And so when we look down here, we can see it compared to water. And so in the case of water, water is actually makes this appear less strong, doesn't it? Because OH minus is a much stronger base than Cn minus. And so yes, it is not that strong of a base. It is definitely a weaker acid. It's a weak acid, and it's on the weaker side of weak acids, right here. And yes, this would be on the stronger sides of bases, but OH minus, which is the basic form of water, is much stronger. So OH minus is stronger base than Cn minus. That's actually the cutoff for strong bases. That's the definition of strong bases. And Cn minus would be a stronger base than water, which is why the HCN is actually an acid. So let's talk about some more salts that can produce acid solutions. The salts in which an anion is not a base and the cation is a conjugate acid of a weak base will actually be acidic salts. They'll be salts that will cause the solution to be acidic. A great example of this is ammonium chloride. So here we have ammonium. Ammonium is actually the conjugate acid of ammonia, which is a base. And so yes, this right here, this NH4 plus is an acid. The Cl minus is negligible. It doesn't really do anything here. Because again, that's the conjugate base of a strong acid, right? So the salts that contain highly charged metal ions can also act as acids. So a great example of this is the aluminum chloride right here, which if you put in solution, this doesn't have any H plus in it. See that? That doesn't have any H's at all in it. But the aluminum is so highly charged that it acts as a charge center, and this can attract the hydrate ions to it, meaning that it will actually make the water itself act as an acid. It will actually make the water give up H pluses because it's such a strong positive center. Any OH minuses get removed from solution, if you will. That's your best analogy in this case. It's actually a little bit more complicated, but that's really more of an advanced inorganic to fully understand it. The best analogy would be that this helps to remove the OH minuses from solution. by binding them to the aluminum 3 pluses. This could have been iron 3 plus. Any of those things would do it. Okay. If you want a more detailed explanation, the sort of basics framework of that is that the hydrates, the water molecules, will actually bind to the aluminum first. And it makes them more stable when they lose their H pluses. That's a sort of framework of that. Okay, anyways, so let's go ahead and look at this. This is going to be the same sort of example we've seen before. Let's calculate the pH of 0.1 molarity, NH4Cl. Remember, that is a salt or an ionic compound. The key Kb value for the NH3, which would have been the basic version of NH4, right, is 1.8 times 10 to the negative 5. So again, we look at our major species, NH4 plus, Cl minus, and H2O. So the NH4 plus and H2O, these can both give off H pluses. However, we've seen a Kb for this value, and the NH4 plus ion is more likely to dissociate and have an H plus come off. So right here we see this NH4 plus losing a proton is acting as an acid. This would be its Ka expression right there. Again, products of reactants, just like every other time. All right, now we have been given the Kb value for the NH3, so you're going to just do what you did before, and that's you're going to take Kw divided by Kb, and that will give you your Ka, which is this right here. So again, Kw divided by that Kb you're given, and that's the Ka for NH4 plus. So NH4 plus is a very weak acid. It is, however, stronger than H2O. Remember, H2O is 10 to the negative 14. So H2O is very, very, very weak acid, okay? Takes a lot to be weaker than that. So again, the focus of this reaction is going to be the NH4 plus. And so again, we have our NH4 plus. That was our initial concentration from the salt. Remember, salts are going to dissociate. And so that will give us 0.1 molarity. Again, we're going to lose some amount of that, so minus x. And whatever we lose of that, whatever we use, is going to be created for the H plus and the NH3. That is going to be what we produce. And so we plug those values in just like before. And again, we have that 0.1 minus x. Well, this is a really small value. It's probably not going to make any difference right there. So we can go ahead and get rid of it. And we go ahead and solve it, and that value is very small, right? That's less than 5% of this value right here. And so that's fine. That approximate rule is fine. And so our H plus concentration is going to be 7.5 times 10 to the negative 6 molarity, which is what we get when we solve for that x. If we take the negative log of that, we'll get the pH, which is 5.13. And of course, that is acidic. We added something that we thought was an acid, and is an acid. And so excellent, great. We got the answer we would expect. All right, so these are the qualitative relationships between the pH and the Ka versus Kb. If your Ka is greater than your Kb, then the pH is going to be less than 7, it'll be acidic. If your Kb is greater than your Ka, then it's going to be basic, greater than 7. If they're equal, then you just found something neutral, which at 25 degrees Celsius would be pH 7, right? So let's predict whether an aqueous solution of each of the following salts would be acidic, basic, or neutral. So first here, this salt is NH4 plus right there. And right there is the acetate anion. So we're going to compare those Ka and Kb for these. Okay, so in here we have NH4 plus again. And this is going to be the cyanide anion right there, Cn minus. So here we have the ions. We've looked up the Ka for that is this. The Kb for this is right there. And we see here that these are actually equal, aren't they? And so in this case, the solution should actually be neutral, pH 7. Okay, so now we have these. We go ahead and get to our table. We again have our value of NH4 plus. We can find the Kb for Cn minus from the Ka of HCN. Again, Kw divided by Ka gives us that value. We notice that this value of Kb is larger than the Ka, isn't it? So since that Kb is larger, and quite a bit larger, I mean, we're talking 100,000, factor of 100,000 or so, this is actually going to be basic solution because the Kb is larger, right? Meaning more base, stronger base. All right, so if the solid sodium cyanide is dissolved in pure water, will the resulting solution be acidic, basic, or neutral? So again, what you're looking at here is Na+. Well, that's actually negligible. That's one of those strong acids, strong bases, cation in this case, of a strong base. This right here is going to be your cyanide. That's that Cn. That's a weak base, isn't it? And so you would expect this to be basic. If the solid ammonium fluoride, NH4 plus and F minus, that's the two ions there, is dissolved in pure water, will the resulting solution be acidic, basic, or neutral? And they've given us our NH3 and HF, the Kb for NH3 and the Ka for HF. So this actually has sort of three parts, doesn't it? You have to take this value, take the Kw divided by this value, then you need the Kw divided by this value. This will give you your Ka for NH4 plus and your Kb for the F minus then. And what we see here is this would then be acidic. Now let me point out a little factor here, if you will, that since this right here is going to be the acid and this right here is going to be the base, we can actually directly compare these and just swap the result. So we know that these are going to be inverses, right? That these are going to be backwards, right? So if we just looked at this Kb versus Ka, we would see Kb is larger than Ka in this case. We know that has to be the opposite. So Kb being larger than Ka would normally mean basic, right? We flip that, it's acidic. Okay? Do you understand what I'm saying? Well, you can't answer me, but hopefully you understand what I'm saying here, that you're doing the opposite. Both of these will be Kw divided by before you look at them. So they're going to proportionally both change the same. All right, so the factors that determine whether a molecule contains an XH bond and behaves as a Bronsted-Lowry acid are going to be the bond strength and the bond polarity. And so your classes of acids, your hydrogen halides, oxyacids, hydrated metal ions, these are all based on these same factors, the bond strength, the bond polarity. So first we see the bond strength. If it's too strong of a bond between the hydrogen and whatever it's bonded to, you can't break it. It's too hard to break. It takes too much energy to break. And so you end up with a weak acid. Because for a strong acid, you have to be able to break that bond, don't you? You have to be able to dissociate it. And so right here we see HF. It has a very strong bond compared to these. And that is a weak acid. HCl, HBr, and HI all have weaker bonds. And so those are stronger acids. They're all strong acids, by the way. Oxyacids, these contain groupings of HOX. So for a given series, the acid strength will increase with increasing number of oxygen atoms attached to that central atom, so attached to the X here. So for example, you may have seen CLO, ClO2, ClO3. The more oxygens you add to that, the stronger the acid becomes. When you're talking about CO, which would be in alcohols, versus COOH, are talking about there, well, COOH is a weak acid. We already know that, right? We've seen that. That's the acetic acid, formic acid we were talking about. Whereas the COH would have just been an alcohol that's not an acid. So again, acid strength is successfully greater than more the number of oxygen atoms. That's why SO3 is a weak acid, SO4 is a strong acid. That's why the NO2 is a weak acid, NO3, strong acid, etc. These are going to actually have two really major effects to this. This is both going to weaken and polarize that OH bond. So first off, how does it polarize it? Well, the more oxygens on this X, the more positive this becomes. And the more it can draw electrons away from this, meaning it's more and more and more polar. Now, it's also going to weaken this because you're going to have less electrons being able to contain this. It's going to weaken this bond. It's also going to have a resonance effect. You may remember resonance. I introduced it to you at the beginning of the semester, and last semester you should have gotten some of that. And that will actually also act to weaken that bond as well and stabilize the resulting negative charge. Something that you don't get total on these. But okay, so here's examples of the chlorines. ClO4, ClO3, ClO2, ClO. And this right here, this is a strong acid actually. And then these are weaker acids. These are weak acids right here. There you go. Right here we see our SO4s and NO3s, like I said before. And this just shows you the example. Okay. And again, these are showing you the electronegativities of these atoms right here due to the fact that they're bonded to the oxygens. They're being more electronegative than normal. You can see the electronegativity directly correlates to the Ka. So it is a stronger acid the more electronegative that atom is typically. The hydrated metal ions. These are going to exhibit behaviors similar to the oxyacids. The greater the charge on the metal ion, the more acidic the hydrated ion becomes. Alright, so the hydrated metal ions, this is kind of what I was describing before, where I was talking about how you can get a metal ion that's going to have waters attached to it. And these waters, of course, the oxygens are going to associate with that positively charged metal ion. That's going to make that more and more positive, much like the oxy acids were. And so you're going to get this greater charge in the metal ion, the more acidic the hydrated ion will become. And so if you get a larger charge on something, so at 2 pluses, usually you're not going to see any of this, okay? 3 plus metal ion, you'll start seeing these effects. You get something like a 4 plus metal ion, you're going to really start seeing it, okay? And that's what I'm talking about there. Now, which factors below are going to determine whether a molecule containing X-H bond will behave as a Bronsted-Lowry acid? So whether that H plus is going to come off easily or not. Well, we mentioned before that the strength of the bond matters, doesn't it? So yes, the strength of the bond will matter. That's going to be your major factor when you're talking about an HX. So let's talk a bit more about this acidic strength in oxides. So if the compound containing the HOX group will produce an acidic solution in water if the OX bond is strong and covalent. A basic solution in water if the OX bond is ionic. Well, think of it this way. If you have sodium hydroxide, that's a strong base, isn't it? But if you have a chlorate, so ClO4, let's say, and that has an H on it, well, that's an acid. That's actually a strong acid. And so that's the difference there. That's a strong covalent bond between that X, the Cl in this case, and the oxygen, versus an ionic bond, which is going to be something like your sodium hydroxide, right? The high electronegativity of your X is actually going to be what will lead to that covalent and strong OX bond. So a low electronegativity will lead to an ionic and weak OX bond. So metals, this is typically this one right here. If you're talking about a large electronegativity non-metal, that's typically this case up here. So the acid oxides, these are going to be formed when covalent oxides are dissolved in water. This is going to lead to the formation of an acidic solution. The OX bond remains intact in these cases. So examples of this are things like SO2, CO2, NO2. You may have heard of the acidification of the ocean. Well, guess what? That's the acidification of the ocean right there, CO2. You may have heard of acid rain. This is actually the cause of acid rain right here. And you may know that stings, if you ever go to a place with a lot of smog, you can't breathe the air, it will actually sting your lungs. It may actually damage and scar it as well, if it's bad enough. And that's actually what you're dealing with here, which is NO2 when it forms in water, when it gets moisture droplets. You end up forming nitric acid, which will actually scar the person's lungs. So basic oxides, you actually probably have experienced quite a few of these basic oxides before. You may not have known it though. So the ionic oxides will dissolve in water to form basic solutions. So if you have something like K2O or calcium oxide, which is a very commonly used antacid, you typically see these as different types of bases. You actually put them in soil to increase the basicity of the soil. That's one of the major uses for them. Oxide ions are going to have high affinity for the protons and are going to react with water to produce the hydroxide ions. So when you react with water, you get hydroxide. Lewis acids and bases. This is the one that, if you remember anything from this course, really you should remember the three-dimensional structures of molecules and Lewis acids and bases. Because most of you are probably going on to organic chemistry of some sort. And these are the two that if you really understood tetrahedral geometry, etc., and you really understood Lewis structures really well, and their VSEPR shapes really well off of that, electron domains, and you really understand Lewis acids and bases, you honestly have a good 30% of organic chemistry nailed out and done. It's really, you're just going to be using these same concepts over and over and over, especially for the first semester. Even for the second semester, though, you honestly will still use these a tremendous amount. And so this is one of the things I would very much recommend if you're moving on with your career in chemistry to go into med school, etc. Pay a little extra attention to, put a bookmark there, make sure those notes are available. The Lewis acids, this is going to be an electron pair acceptor. Now, this is a bit different because before we talked about donating H+. It's a little related though. Sometimes they actually can be, you can have something that's both a Bronsted-Lowry and a Lewis acid, but this is a completely different take on it, right? So in this case, you have something positive that can accept an electron pair. This is going to contain an empty atomic orbital that can be used to accept that electron pair from your Lewis base. A Lewis base will be able to donate an electron pair. So it will have an electron pair to donate. So it'll be an electron pair donor. The basic oxides, ionic oxides dissolve in water to form basic solutions. So some of the examples of these are, did I just go back up? I did, sorry. I guess I am stuck in a loop. That's not good. All right, so these are the three different models for acids and bases. They're a little summary in my little table here, and honestly, they're pretty easy to remember as long as you just play with them, practice a little bit. Try to use the definitions. Like learning a word on a day on those calendars, right? Use it. Lewis model and Bronsted-Lowry acid-base reactions here. So this right here is going to be a reaction between a proton and a Lewis and a ammonia right here, right? And it gives you the ammonium anion, right, or ammonium cation, sorry, right here that we've been looking at several times throughout this lecture. And so right here we can actually see, well, this is actually a Lewis acid right here, this H plus. And this has a lone pair it is donating, so this right here is a Lewis base. Now, this also fulfills the Bronsted-Lowry definition. So this right here is donating an H plus. This right here is accepting an H plus. So this is one of those cases where both actually make sense. Let's look at a case where we don't fulfill the Bronsted-Lowry definition. So right here is a great example. We have BF3. This has a very positively charged boron right here. This can accept a lone pair of electrons, so it is a Lewis acid. This right here, ammonia, this can donate a lone pair of electrons, so this is a Lewis base. You get this reaction right here. Congratulations, you've just done a Lewis acid and base reaction. And we're getting ready for organic chemistry right here. All right, now, this right here is going to be a hydration of a metal ion that we talked about before. So here we have aluminum 3 plus. It's going to take up 6 water molecules that are going to be waters by hydration, if you remember those. And so it'll make this complex right here. This complex right here is actually acidic according to an Arrhenius and a Bronsted-Lowry definitions of an acid. However, this reaction here that makes it is actually a Lewis acid and base reaction. You can see here your Lewis acid is going to accept an electron pair. And that's how you create this complex here. So isn't that fascinating? All right, so here we see an example of a covalent oxide and water. So here's the covalent oxide. We add that in to water, and we get right here H2SO4, which is sulfuric acid, a strong acid. And this happens through a Lewis acid-base reaction, which is this one right here. This is a positively charged sulfur. This is a partially positively charged sulfur that is going to be able to take up a lone pair of electrons from the Lewis base. Okay, so for each reaction, identify the Lewis acid and base. Hopefully this is pretty obvious to you guys when you look at these. Lewis base has to have lone pairs of electrons. Positive things normally do not have lone pairs of electrons. So this right here, this is the Lewis. Let me just go down to this. This right here is your Lewis acid. It's going to take on these lone pair of electrons right here, which is your Lewis base. So right here we see the other example, which is our H plus is again our Lewis acid. This right here will be our Lewis base because again it has a lone pair of electrons that you can now see nicely, right, when I put up those figures. Alright, so when you're analyzing an acid-base equilibrium problem, one of the most important steps to dealing with the problem is one of the steps that I probably make look kind of easy, but it takes a little bit of thought on your guys' part because you're not really used to it, right? And that's the analysis that's done at the beginning of the problem. That's really the imperative part that's really probably going to determine whether you get these problems right or wrong. And the deal is, is that this is actually, when it comes down to real world problem solving and just in general problem solving, word problem solving, but really I stress real world problem solving. These are the skills that you really need. This is really what you're trying to build by doing science courses here. The specific how to solve each little problem in a formulaic method is not. That's not actually the most important part. It's this ability to take and synthesize information I give you to solve a real world problem. Which, by the way, all of the problems I give you almost across the board are actually based on real world problems. So I typically make them a little bit easier sometimes by, giving you guys constants and everything, so you don't have to look them up and trying to reduce the work, but that's about it. So note the major species present in the solution. Determine if your reaction will go to completion. Ascertain the equilibrium that dominates the solution. These are all things we practice doing like half a dozen times in the course of this lecture, but those are the parts that you probably skimmed over when I did them, but you really should be testing yourself on, okay? That you should pause the video, go back, look at the problem, see if you can do that, and then see how I do it on the next page. Don't just flip over to the next page, okay? Okay, folks, take care. That's this lecture, and I will try to get the next lecture right away.